In the vastness of space, our blue marble hangs suspended against the infinite black. From this cosmic perspective, Earth appears as a fragile oasis, a tiny island in an ocean of darkness. This is our home, the cradle of humanity. But our curiosity reaches far beyond its boundaries. For thousands of years, we have gazed at the stars and wondered what lies beyond our world. We have mapped the night sky, tracked the movements of planets, and dreamed of exploration. In the modern era, this ancient curiosity has taken physical form as we have built machines to be our eyes and ears in the cosmos. These robotic explorers, these mechanical emissaries, have traveled where no human could survive. They have journeyed for decades through the harshest environments imaginable, all to satisfy our profound need to understand the universe around us. They transmit their findings back to Earth in whispers of radio waves, traveling across millions of kilometers of empty space, bringing us knowledge that reshapes our understanding of our cosmic neighborhood. Picture yourself floating gently above Earth. From here, you can see the delicate blue atmosphere that protects all life below. Now imagine drifting further away, watching as our planet shrinks to a pale blue dot, just as astronomer Carl Sagan once described. Continue outward, past the Moon, past Mars, beyond the asteroid belt, and into regions where the Sun appears as just another star in the sky. It is here, in these distant realms, that our most adventurous spacecraft now travel. Some have completed their primary missions decades ago, yet continue to function, sending back data from regions no human has ever visited. They are the pioneers of our solar system and beyond, the furthest extensions of human presence in the cosmos. The Voyagers, the Pioneers, New Horizons. These names may sound like simple designations, but each represents a triumph of human ingenuity and technical prowess. Each carries with it a piece of humanity, physical tokens of our existence, and each continues a journey that will likely outlast our civilization. These spacecraft are more than just collections of metal, silicon, and plastic. They are the embodiment of our desire to reach beyond ourselves, to touch the unknown, to understand our place in the universe. They carry our questions into the void and return with answers we could never have imagined. As we contemplate these distant travelers, we might feel a sense of both insignificance and profound connection. Insignificance because the distances they traverse remind us of how small we truly are in the cosmic scale. Connection because through them, we extend our presence across the solar system and into interstellar space. Consider the immensity of their journeys. Voyager 1, our most distant explorer, has traveled over 23 billion kilometers from Earth. Light itself, the fastest thing in the universe, takes over 20 hours to reach it. The radio signals it sends back to us travel at this same speed, meaning that when we receive a message from Voyager, we are hearing its voice from nearly a day ago. By the time we respond, another day will have passed. This is conversation across the void, patient and deliberate, stretched across time, in a way that reminds us of our limitations. Yet despite these vast distances, our connection remains. The spacecraft continue to speak to us, their aging systems still functional after more than 4 decades in the harshest environment imaginable. They endure radiation, cosmic dust, the near absolute zero of space, and still they function, still they observe, still they teach us about realms we can otherwise only imagine. The technology that powers these distant travelers would seem primitive by today's standards. The computer on board Voyager has less processing power than a modern digital watch. The camera that captured some of the most iconic images in the history of space exploration has a resolution lower than the first cell phone cameras. And yet, these simple machines have revealed to us the complexity and beauty of our solar system in ways that have transformed our understanding of our cosmic home. Think of what these machines have witnessed. They have seen the swirling storms of Jupiter, a planet so large that all other planets in our solar system could fit inside it. They have revealed the intricate beauty of Saturn's rings, made of countless icy particles orbiting in perfect harmony. They have shown us Uranus and Neptune, ice giants that had never been visited before. And beyond these worlds, they have measured the very fabric of space itself, the invisible fields and particles that make up the medium between the stars. In this gentle exploration, we will follow the journeys of our most distant robotic explorers. We will discover what they have taught us about the outer planets, the edge of our solar system, and the mysterious region where our sun's influence gives way to interstellar space. We will contemplate the messages they carry, intended for other intelligent beings who might one day encounter them in the vastness of space. So close your eyes if you wish, and let yourself drift outward with these silent travelers. Feel the gradual cooling as you move away from the sun. Experience the thinning of the solar wind, and imagine what it might be like to leave our solar system entirely, to enter the vast ocean of space between the stars. This is the journey of our most distant emissaries, a story of discovery, perseverance, and the quiet grandeur of space exploration. This is the story of humanity's reach, extending far beyond our small world, touching the stars. In the summer of 1977, as people on Earth went about their daily lives, two remarkable machines lifted off from Cape Canaveral, Florida, beginning what would become the greatest journey of exploration in human history. Voyager 2 departed first on August 20th, followed by Voyager 1 on September 5th. This seemingly backward order was intentional, as Voyager 1 would travel faster and eventually overtake its twin, becoming the most distant human-made object in existence. The Voyager spacecraft were designed to take advantage of a rare alignment of the outer planets that occurs only once every 176 years. This cosmic arrangement would allow them to use the gravity of each world they visited to slingshot toward the next, gaining speed without consuming precious fuel. Scientists called this the Grand Tour, an unprecedented opportunity to visit Jupiter, Saturn, Uranus, and Neptune in a single mission. Each Voyager probe weighs approximately 825 kilograms, about the size of a small car. They were built to last 5 years, with a hope they might survive long enough to reach Saturn. Yet, remarkably, almost 50 years later, they continue their journey, sending data back to Earth from the frontier of interstellar space. The origin of the Voyager missions can be traced back to the 1960s, when a young NASA engineer named Gary Flandro was calculating potential trajectories for spacecraft. Flandro discovered that during the late 1970s, the 4 giant planets of our solar system would be arranged in a way that would allow a spacecraft to visit each one using a technique called gravity assist. This technique, sometimes described as a cosmic billiard shot, uses a planet's gravity to accelerate a spacecraft and bend its path. Without this alignment, visiting all 4 outer planets would require prohibitive amounts of fuel and decades of additional travel time. When NASA leaders understood the significance of this rare alignment, they began planning an ambitious mission originally called the Grand Tour. Budget constraints nearly cancelled this dream, but a scaled-down version was eventually approved as the Mariner Jupiter-Saturn mission, later renamed Voyager. Despite the budget reduction, the spacecraft was still designed with the capability to reach Uranus and Neptune if they remained operational after Saturn. The construction of the Voyager spacecraft represented the pinnacle of 1970s technology. Each carries 11 scientific instruments, including cameras, spectrometers, magnetometers, and particle detectors. Their primary radio antenna is a dish 3.7 meters in diameter, capable of communicating with Earth across billions of kilometers of space. The signals they send are incredibly faint by the time they reach us, with a power of just 10 to the negative 16 watts, 10 billion times weaker than the power of a typical watch battery. Yet NASA's Deep Space Network, with its giant radio antennas up to 70 meters in diameter, can still detect these whispers from the edge of our solar system. Power for these distant explorers comes from radioisotope thermoelectric generators, or RTGs. These remarkable devices contain plutonium-238, which naturally produces heat as it radioactively decays. This heat is converted directly into electricity by an array of thermocouples, providing a steady, reliable power source that requires no sunlight, no moving parts, and can function for decades. Even now, 48 years after launch, the RTGs continue to produce enough power to operate critical systems, though at gradually diminishing levels. Perhaps the most remarkable feature of the Voyagers is their computer system. The primary computer on each spacecraft has less memory than a modern digital key fob, just 8,000 words of processing memory. Yet with this minimal computing power, the Voyagers can control their orientation in space, focus their instruments on targets of interest, process and compress the scientific data they collect, and manage their communications with Earth. They are a testament to how much can be accomplished with elegant, efficient engineering. The journey to Jupiter, our solar system's largest planet, took Voyager 1 about 1.5 years. As it approached the giant world in March 1979, the spacecraft began sending back images that stunned scientists and the public alike. Jupiter revealed itself not as a static, striped ball, but as a dynamic, churning world of storms and swirling clouds. The Great Red Spot, a storm larger than Earth that had been observed for centuries, was shown in unprecedented detail. Scientists saw that it rotated counterclockwise, with winds reaching speeds of 400 kilometers per hour. The entire planet, they discovered, was wrapped in thousands of kilometers of complex, turbulent clouds, composed largely of hydrogen and helium, with traces of methane, ammonia, and water vapor. The Voyager cameras revealed that Jupiter's cloud bands, the alternating light and dark stripes visible even in small telescopes, are actually complex weather systems. The lighter zones are regions where gas is rising, while the darker belts are areas where gas is sinking. The boundaries between these regions generate enormous turbulence, creating swirling eddies and storms that can persist for years or even centuries. The interaction of these weather systems, combined with Jupiter's rapid rotation, just under 10 hours for a complete turn, creates wind patterns unlike anything seen on Earth. Beyond the visible clouds, Voyager discovered that Jupiter possesses a powerful and complex magnetic field, 10 times stronger than Earth's. This magnetic field traps charged particles from the solar wind and from volcanic material ejected by the moon Io, creating radiation belts so intense they would deliver a lethal dose to a human in minutes. This radiation proved challenging, even for Voyager's hardened electronics, requiring special shielding to protect the delicate instruments. But perhaps the most surprising discovery came from Jupiter's moons. The Galilean satellites, those 4 large moons discovered by Galileo in 1610, proved to be worlds in their own right, each completely different from the others. Io, the innermost large moon, revealed itself as the most volcanically active body in our solar system. As Voyager 1 passed, it captured something scientists could scarcely believe: actual volcanic eruptions in progress. Plumes of material were being ejected hundreds of kilometers into space. Later analysis showed that tidal forces from Jupiter's immense gravity kneaded Io's interior, generating tremendous heat that melted rock into magma. The surface of this remarkable moon is constantly being resurfaced by sulfurous eruptions, a landscape of yellows, oranges, and reds, unlike anything seen on Earth. The discovery of Io's volcanism was one of the greatest surprises of the Voyager mission. Until that moment, active volcanism had only been known to exist on Earth. The realization that other worlds could be geologically active forced scientists to reconsider their understanding of planetary bodies throughout the solar system. The volcanoes of Io erupt material rich in sulfur compounds, creating a thin atmosphere and contributing to a donut-shaped region of charged particles that encircles Jupiter, known as the Io plasma torus. Europa, the second Galilean moon, presented a completely different appearance. Its surface is one of the smoothest in the solar system, a global shell of ice crisscrossed by a complex network of fractures. These features suggested to scientists that beneath this frozen crust might lie a global ocean of liquid water, kept warm by the same tidal forces that heat Io. The possibility of a vast, dark ocean hidden beneath the ice immediately raised tantalizing questions about the potential for life. The fractures on Europa's surface, some extending for thousands of kilometers, often appear in parallel sets or as complex, intersecting patterns. They resemble the cracks that form in sea ice on Earth when underlying currents cause the ice to flex and break. Some regions show what appear to be ice rafts, angular blocks that seem to have broken apart and shifted position before refreezing. All these features strongly suggest that Europa's ice shell is relatively thin and overlies a mobile layer, most likely liquid water. Ganymede, the largest moon in our solar system, larger even than the planet Mercury, showed a complex terrain of dark and light regions, suggesting a long history of geological activity. Voyager's cameras revealed an ancient surface divided between darker, heavily cratered regions and lighter areas marked by parallel grooves and ridges. These grooved terrains, which cover over half the surface, appear to have formed through tectonic processes, as Ganymede's crust stretched and fractured. Later missions would discover that Ganymede possesses its own magnetic field, the only moon known to do so, implying a molten iron core within this giant satellite. And Callisto, the outermost Galilean satellite, revealed an ancient surface covered in countless impact craters, a record of 4 billion years of meteorite bombardments. Unlike its sibling moons, Callisto shows no signs of significant geological activity, appearing as a time capsule from the early solar system. Its most distinctive feature is a huge bullseye pattern called Valhalla, a multi-ring impact basin stretching 2,000 kilometers across, created when a massive asteroid or comet struck the moon billions of years ago. After their encounters with Jupiter and its moons, both Voyager probes set course for Saturn, reaching the ringed planet in 1980 and 1981. Saturn had been observed from Earth for centuries, its magnificent rings visible even in small telescopes. But what Voyager revealed was a system of breathtaking complexity that far exceeded astronomers' expectations. Instead of the handful of rings visible from Earth, Voyager showed thousands of individual ringlets. These structures, composed of countless particles of water ice ranging in size from microscopic dust to house-sized boulders, orbit Saturn in an intricate cosmic dance. Gravitational interactions create waves, braids, and gaps in the rings, a constantly changing pattern of stunning beauty. The rings of Saturn span a distance of about 280,000 kilometers from the innermost to the outermost edge, yet they are astonishingly thin, perhaps as little as 10 meters in some places. This gives them a remarkable profile when viewed edge-on, appearing almost as a razor-thin line cutting across the planet. Voyager discovered that despite their solid appearance when viewed from a distance, the rings are actually about 99% empty space, their particles spread out with considerable distance between them. One of the most fascinating discoveries was the role played by small shepherd moons. These tiny satellites, some just a few kilometers across, orbit within or near gaps in the rings. Their gravity helps to maintain the sharp edges of these gaps, herding ring particles like cosmic sheepdogs, maintaining their flock. In some cases, the gravitational influence of these moons creates waves and ripples in the ring material, visible as scalloped edges or spiral patterns. Beyond the rings, Saturn's atmosphere displayed subtle bands of clouds and occasional storms, though less dramatic than Jupiter's. The planet's largest moon, Titan, particularly intrigued scientists. Larger than Mercury, Titan is unique among moons in having a substantial atmosphere, denser even than Earth's, and composed primarily of nitrogen. Voyager could not see through this hazy orange atmosphere, but its instruments detected complex organic molecules forming in the moon's upper air, hinting at a world of exotic chemistry that would later be explored by the Cassini-Huygens mission. Voyager also discovered several previously unknown moons orbiting Saturn, bringing the known total at the time to 17. Among these was Enceladus, a small, ice-covered moon that showed signs of unusual geological activity. Later missions would reveal that Enceladus, like Europa, likely contains a subsurface ocean, and even more remarkably, ejects plumes of water vapor and ice particles through cracks in its icy crust. After Saturn, the paths of the two Voyager spacecraft diverged. Voyager 1's trajectory bent northward out of the plane of the planets, beginning its journey into interstellar space. Voyager 2, meanwhile, continued on to Uranus, arriving in January 1986, 9 years after launch. Uranus presented a very different kind of planet. While Jupiter and Saturn are primarily composed of hydrogen and helium, Uranus belongs to a class known as ice giants. Beneath its atmosphere lies a vast mantle of water, ammonia, and methane ices, though not in solid form. These materials exist in a superheated, highly compressed state unlike anything on Earth. The most striking feature of Uranus is its extreme tilt. While most planets spin roughly upright, with their equators near the plane of their orbit, Uranus lies nearly on its side, rolling along its path around the Sun like a ball. This unusual orientation, which causes the planet to experience seasons unlike any other world in our solar system, is thought to be the result of a catastrophic collision with an Earth-sized object early in the solar system's history. Voyager 2 revealed that, despite its odd orientation, Uranus has a magnetic field, though strangely tilted and offset from the planet's center. The spacecraft also discovered 10 previously unknown moons orbiting the planet, bringing the known total at that time to 15, and found a system of dark rings much less prominent than Saturn's. The atmosphere of Uranus appeared blandly uniform to Voyager's cameras, a featureless blue-green sphere showing none of the dramatic cloud patterns of Jupiter or Saturn. This lack of visible features was initially disappointing to scientists, but later analysis revealed that Voyager had arrived during Uranus's southern summer, when one pole had been facing the Sun continuously for decades. This created a relatively stable atmospheric pattern with few visible features. Subsequent observations from Earth, as Uranus moved along its 84-year orbit, have shown that when the seasons change, the planet's atmosphere becomes more dynamic, with storms and cloud patterns emerging. The moons of Uranus proved more interesting than the planet itself. Miranda, the innermost of the 5 large satellites, showed a bizarre, jumbled terrain unlike anything else in the solar system. Its surface appears to be a patchwork of different terrains, with some regions heavily cratered and others showing systems of ridges and valleys. One area, nicknamed the Chevron, features cliffs up to 20 kilometers high, among the tallest known cliff faces in the solar system. These strange features suggest that Miranda may have been completely shattered by a massive impact early in its history, then reassembled in a jumbled fashion. The other major moons, Ariel, Umbriel, Titania, and Oberon, each showed distinct characteristics. Ariel has the youngest surface, with relatively few impact craters and signs of past geological activity. Umbriel, by contrast, is dark and heavily cratered, appearing to have undergone little change since its formation. Titania and Oberon, the largest of Uranus's moons, show a mix of impact craters and signs of past internal activity, including fault systems that created valleys up to hundreds of kilometers long. After its Uranus encounter, Voyager 2 journeyed on to Neptune, reaching our solar system's most distant major planet in August 1989, 12 years after leaving Earth. Despite being 4.5 billion kilometers from the Sun, receiving only 1/900th the sunlight of Earth, Neptune revealed itself as a surprisingly dynamic world. Voyager discovered the Great Dark Spot, a massive storm system reminiscent of Jupiter's Great Red Spot, and measured the fastest winds in the solar system, reaching speeds of 2,100 kilometers per hour. The planet's atmosphere, tinged blue by methane gas, showed multiple cloud layers and storm systems that scientists had not expected to find in such a cold, distant world. Unlike the relatively featureless Uranus, Neptune's atmosphere displayed a remarkable array of visible weather patterns. White, high-altitude clouds of methane ice were seen casting shadows on the deeper cloud layers below, allowing scientists to measure the altitude and structure of Neptune's atmosphere. These clouds often formed and dissipated over periods of just hours or days, indicating a much more dynamic weather system than expected for a world so distant from the Sun. Scientists concluded that Neptune must have some internal heat source, leftover energy from its formation, that drives these weather patterns despite the minimal solar energy it receives. Neptune's largest moon, Triton, proved especially fascinating. It orbits the planet in a direction opposite to Neptune's rotation, suggesting it was captured rather than formed alongside its parent planet. Most remarkably, despite surface temperatures of -235 degrees Celsius, Voyager 2 observed actual geysers erupting from Triton's south polar region, spewing nitrogen gas and dark particles 8 kilometers high. Triton's surface is primarily composed of nitrogen ice, with smaller amounts of methane and carbon dioxide ice. The spacecraft revealed a varied landscape with relatively few impact craters, suggesting that the surface is geologically young and actively being resurfaced. One distinctive terrain type, described as cantaloupe terrain due to its resemblance to the skin of that fruit, consists of a complex pattern of ridges and depressions, unlike anything seen elsewhere in the solar system. The nitrogen geysers appear to be driven by a greenhouse effect, where the weak sunlight passes through a thin layer of clear nitrogen ice, warming the darker material beneath. This creates pressure that eventually erupts through the ice in spectacular plumes. Voyager also discovered 6 previously unknown moons orbiting Neptune, bringing the total at that time to 8. These smaller moons are irregularly shaped and appear to be captured asteroids rather than bodies that formed alongside the planet. As Voyager 2 pulled away from Neptune, it captured a farewell image of the planet silhouetted against the distant sun. This poignant view marked the end of the Grand Tour. No new planets awaited the spacecraft. Like its twin, Voyager 2 was now bound for interstellar space. But the most historic moment for the Voyager program was yet to come. On August 25, 2012, Voyager 1 crossed a boundary that no human-made object had ever reached. It passed through the heliopause, the limit of the sun's influence, and entered interstellar space. Voyager 2 followed suit in November 2018. This transition was not marked by any visible landmark, of course, but by subtle changes in the particles and magnetic fields detected by the spacecraft's instruments. Throughout the solar system, the sun emits a stream of charged particles called the solar wind, which creates a bubble around our planetary system called the heliosphere. At the edge of this bubble, the outward pressure of the solar wind balances against the inward pressure of the interstellar medium, the thin gas and dust that fills the space between stars. When the Voyagers crossed this boundary, they detected a sharp drop in solar particles and a corresponding increase in galactic cosmic rays, high-energy particles from distant stars and galaxies. The Voyagers continue to make discoveries even now. They have revealed that the boundary between our solar system and interstellar space is not a simple, smooth transition, but a complex region where the outward pressure of the solar wind meets the inward pressure of the interstellar medium. They have detected the faint sound of plasma waves, the vibration of electrons in the thin gas between the stars, and they have measured an increase in high-energy cosmic rays that had previously been deflected by the sun's magnetic field. As they journey onward, their power systems gradually failing, the Voyagers will fall silent sometime around the year 2025, yet they will continue their silent flight through the galaxy. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 725. Long after Earth itself has changed beyond recognition, these quiet ambassadors will carry their message of a small, curious species that once reached out to touch the stars. Before the Voyagers ventured into the outer solar system, another pair of spacecraft blazed the trail. Pioneer 10 and Pioneer 11 were humanity's first emissaries to the distant planets, the first human-made objects to cross the asteroid belt, the first to encounter Jupiter and Saturn, and the first to venture into the great unknown beyond. Their story is one of remarkable achievement, unexpected resilience, and the beginning of humanity's physical presence in the outer solar system. The Pioneer program began in the 1950s as a series of lunar probes, but by the late 1960s, NASA's ambitions had expanded to the outer planets. Pioneer 10 and 11, designed as sister spacecraft, would serve as pathfinders, testing whether a spacecraft could safely navigate the asteroid belt and survive the intense radiation environment around Jupiter. These missions were considered so risky that subsequent, more advanced spacecraft like Voyager were only approved once Pioneer had demonstrated such journeys were possible. Pioneer 10 launched on March 2, 1972, atop an Atlas Centaur rocket from Cape Canaveral, Florida. At the time, it was the fastest human-made object ever launched, reaching a velocity of 52,000 kilometers per hour as it escaped Earth's gravitational pull. Pioneer 11 followed on April 5, 1973, on a similar trajectory, but with slightly different objectives. The design of the Pioneer spacecraft was elegant in its simplicity. Each weighed about 250 kilograms, considerably lighter than the later Voyagers. Their distinctive shape featured a 2.7-meter diameter dish antenna that remained permanently fixed on Earth, with instruments mounted on a central compartment behind this dish. Extending from the sides were 4 booms holding scientific instruments away from the main body to reduce interference. Perhaps the most visually striking feature was the pair of radioisotope thermoelectric generators, or RTGs, mounted on a 3rd boom. Like the Voyagers that would follow, the Pioneers derived their electrical power from the heat produced by the natural decay of plutonium-238. This power source was crucial for missions to the outer solar system, where sunlight is too faint for solar panels to generate sufficient electricity. Another distinctive feature was the spacecraft's spin stabilization. Unlike the Voyagers, which used thrusters to maintain a fixed orientation, the Pioneers rotated slowly at about 4.8 revolutions per minute, like a gentle cosmic top. This simple approach provided stability without requiring complex attitude control systems. The scientific payload of each Pioneer was modest by today's standards but revolutionary for its time. Each carried 11 scientific instruments, including magnetometers to measure magnetic fields, charged particle detectors to study radiation, meteoroid detectors to assess the danger of small space debris, ultraviolet and infrared radiometers to study the heat properties of planets, and of course, cameras to capture images. But perhaps the most famous component of the Pioneer spacecraft was not a scientific instrument at all, but a message to the stars. Affixed to each was a gold anodized aluminum plaque, measuring 15 by 23 centimeters, designed to communicate information about humanity to any extraterrestrial intelligence that might someday encounter the spacecraft. Designed by Carl Sagan, Frank Drake, and artist Linda Salzman Sagan, these plaques featured a diagram of a man and woman, a representation of the hydrogen atom, a diagram of our solar system, and a map using pulsars to locate the sun in our galaxy. It was humanity's first physical message sent beyond our solar system, a precursor to the more elaborate golden records later carried by the Voyagers. The primary challenge facing the Pioneer missions was the asteroid belt, a vast ring of rocky debris between Mars and Jupiter. At the time, some scientists feared that the asteroid belt might be impenetrably dense, a barrier of colliding rocks that would destroy any spacecraft attempting to pass through. Pioneer 10's journey would test this hypothesis. As it approached the belt in July 1972, scientists and engineers held their breath. To their great relief, Pioneer 10 passed through the asteroid belt without incident, encountering far less material than feared. The spacecraft detected only a sparse distribution of dust particles, demonstrating that the asteroid belt was actually mostly empty space, with its countless asteroids spread over an enormous volume. This discovery opened the door for all future exploration of the outer solar system, proving that the physical path to Jupiter and beyond was navigable. Pioneer 10's encounter with Jupiter began in November 1973, as its instruments started to detect the giant planet's enormous magnetic field, the largest planetary magnetosphere in our solar system. As it drew closer, the intensity of Jupiter's radiation belts increased dramatically. These belts, composed of energetic charged particles trapped by the planet's magnetic field, proved to be far more intense than Earth's Van Allen belts. Pioneer 10 was exposed to radiation levels that would have been lethal to a human astronaut. Even the hardy spacecraft itself suffered from the intense bombardment. Random electronic errors began to occur as high-energy particles struck its systems. The radiation caused damage to the imaging photopolarimeter, affecting the quality of its images. Yet despite these challenges, Pioneer 10 continued to function, its systems proving more resilient than engineers had dared to hope. On December 3, 1973, Pioneer 10 made its closest approach to Jupiter, passing within 130,000 kilometers of the planet's cloud tops. The images it returned, though primitive by modern standards, gave humanity its first close look at the giant planet. Pioneer's instruments measured Jupiter's magnetic field, studied its atmospheric composition, observed its intense radiation belts, and examined its distinctive cloud bands. These observations transformed Jupiter from a distant astronomical object to a real, complex world, with dynamic systems and characteristics. Pioneer 10's cameras also provided the first close-up views of Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto. Though the images lacked the resolution to reveal the dramatic features later discovered by Voyager, they gave scientists their first glimpse of these diverse worlds. The spacecraft measured their sizes more accurately than had been possible from Earth and detected Io's unusual properties, though it would be left to Voyager to discover the moon's spectacular volcanism. After its Jupiter encounter, Pioneer 10 continued on a trajectory that would take it out of the solar system entirely. It crossed the orbit of Saturn in 1976 and Uranus in 1979, though it did not encounter these planets. By 1983, it had crossed Neptune's orbit, becoming at that time the most distant human-made object in space, a title it would hold until Voyager 1 overtook it in 1998. Pioneer 11, meanwhile, followed a more complex path. After launching in April 1973, it reached Jupiter in December 1974, taking a different trajectory than its predecessor. While Pioneer 10 had used Jupiter's gravity to fling it upward out of the plane of the solar system, Pioneer 11's trajectory was designed to use Jupiter's gravity as a slingshot, bending its path downward and back inward towards Saturn. This gravity assist maneuver, the first of its kind in the outer solar system, dramatically changed Pioneer 11's course and speed without using any fuel. The spacecraft passed close to Jupiter's north pole, providing a perspective completely different from Pioneer 10's equatorial view. The data from this polar pass gave scientists their first three-dimensional understanding of Jupiter's magnetic field and radiation belts. Pioneer 11's encounter with Jupiter was even more daring than Pioneer 10's. It passed just 34,000 kilometers above the planet's cloud tops, enduring radiation levels 3 times higher than its predecessor. The fact that it survived this intense environment gave NASA engineers increased confidence when designing the Voyager missions that would follow. After its Jupiter flyby, Pioneer 11 spent nearly 5 years crossing the vast gulf between Jupiter and Saturn, a distance of over 700 million kilometers. It finally reached the ringed world in September 1979, becoming the first spacecraft to visit Saturn. Just 9 months before Voyager 1 would arrive, Pioneer 11 served as a crucial scout, confirming that the planned Voyager trajectory through Saturn's ring plane would be safe. As it approached Saturn, Pioneer 11 captured the first close-up images of the planet and its magnificent rings. It discovered new rings not visible from Earth and provided data on the composition of the ring particles, confirming they were primarily composed of water ice. The spacecraft studied Saturn's magnetic field, which proved to be stronger than Earth's but weaker than Jupiter's, and measured the planet's atmospheric properties. Perhaps most significantly, Pioneer 11 gave humanity its first glimpse of Titan, Saturn's largest moon, and one of the most intriguing worlds in our solar system. The spacecraft could not penetrate Titan's thick, hazy atmosphere, but its observations confirmed that this moon had a substantial atmosphere, a rarity among the moons of our solar system. This discovery heightened scientific interest in Titan, leading to the later Cassini-Huygens mission that would reveal its lakes of liquid methane and ethane. After its Saturn encounter, Pioneer 11, like its sister craft, continued on a trajectory that would eventually carry it out of our solar system. It crossed the orbit of Uranus in 1986, by which time it was clear that both Pioneer spacecraft would ultimately leave the solar system altogether, becoming interstellar travelers. The technological achievements of the Pioneer missions become even more impressive when we consider the limitations of 1970s technology. The main computer aboard each Pioneer had far less processing power than a modern digital watch. The spacecraft could transmit data back to Earth at a maximum rate of only 2,048 bits per second when near Jupiter, and this rate dropped to as low as 16 bits per second at greater distances. By comparison, a typical home internet connection today operates millions of times faster. Despite these limitations, the Pioneers continued to function and communicate with Earth long after their primary missions were complete. Pioneer 10, designed to last just 21 months, operated for over 30 years. Its last weak signal was received on January 23, 2003, when the spacecraft was 7.6 billion kilometers from Earth. Pioneer 11 remained operational until September 30, 1995, when its power source weakened to the point that its radio transmitter could no longer function. At that time, it was almost 7 billion kilometers from Earth, with its radio signals taking over 6 hours to reach us. The final command to Pioneer 11 instructed it to shut down its transmitter, a poignant moment that marked the end of communication with a spacecraft that had revealed so much about our outer solar system. Though we no longer hear from them, both Pioneer spacecraft continue their silent journeys through interstellar space. Pioneer 10 is following a path that will take it in the general direction of the star Aldebaran in the constellation Taurus. It will pass in the vicinity of this star in about 2 million years. Pioneer 11 is heading toward the constellation Aquila and will pass near the star Lambda Aquila in about 4 million years. The scientific legacy of the Pioneer missions is profound. Before Pioneer, our knowledge of the outer solar system was limited to what could be observed through Earth-based telescopes. After Pioneer, we had direct measurements of Jupiter's and Saturn's atmospheres, magnetic fields, and moons. We understood the true nature of the asteroid belt. We had confirmed that spacecraft could survive in the outer solar system, opening the door for the more sophisticated missions that would follow. Yet beyond their scientific achievements, the Pioneer spacecraft hold a special place in the history of space exploration as true pathfinders. They were the first to venture where no human-made object had gone before, testing the unknown and proving that the seemingly insurmountable challenges of deep space exploration could be overcome. The Pioneer missions also introduced a more philosophical aspect to space exploration. With their gold plaques, they became humanity's first deliberate message to the cosmos, an acknowledgement that our spacecraft might someday be found by other intelligent beings. This concept of spacecraft as cosmic messengers, as ambassadors of Earth carrying information about their creators, would be expanded with the Voyager Golden Records and has become an enduring part of how we think about our robotic emissaries to the stars. There is something particularly poignant about the fate of the Pioneer spacecraft. Unlike missions that end with dramatic impacts or deliberate destruction, the Pioneers simply faded away, their voices growing fainter until they could no longer be heard. Yet they continue their journeys in silence, still faithfully fulfilling their final command to travel outward, away from the sun, carrying their golden messages across the interstellar void. The design of the Pioneer spacecraft themselves incorporated some fascinating innovations that helped them accomplish their groundbreaking missions. Their spin stabilization, for instance, provided a simple yet effective way to maintain orientation in space. By spinning like a top at about 4.8 rotations per minute, the spacecraft achieved gyroscopic stability that kept their radio antennas pointed toward Earth without requiring complex attitude control systems or excessive fuel use. This spinning also allowed the instruments to sweep in a circle, scanning their surroundings as the spacecraft rotated. The power source for both Pioneers, the radioisotope thermoelectric generators, or RTGs, represented a crucial technology for deep space exploration. Each Pioneer carried 4 SNAP-19 RTGs, generating about 160 watts of power at launch. These devices contain plutonium-238, which naturally decays and produces heat. This heat was then converted directly into electricity using thermocouples. The beauty of this system was its simplicity and longevity. With no moving parts to wear out, the RTGs could provide reliable power for decades, though the gradual decay of the plutonium meant that the available power slowly diminished over time. The communication system of the Pioneer spacecraft was another marvel of engineering. The 2.7-meter diameter dish antenna was fixed to the spacecraft body, always pointing in the same direction relative to the stars. This meant that the entire spacecraft had to be oriented to keep the antenna aimed at Earth. The radio signals transmitted by this antenna when the spacecraft were near Jupiter were about as powerful as a refrigerator light bulb. Yet these faint signals could be detected across hundreds of millions of kilometers of space by NASA's Deep Space Network. By the end of the missions, when the spacecraft were billions of kilometers away, the signals arriving at Earth were so weak that they were billions of times fainter than a whisper. The scientific instruments carried by the Pioneers were designed to study a wide range of phenomena. The magnetometer, mounted on a long boom to keep it away from the spacecraft's own magnetic field, could detect the strength and direction of magnetic fields in space. The charged particle detector measured the radiation environment, crucial information for designing future spacecraft that would need to withstand these conditions. An optical system called the Imaging Photopolarimeter served as the spacecraft's camera, though it worked quite differently from modern digital cameras. As the spacecraft spun, this instrument would scan across its field of view, building up images line by line. This process was slow, the equivalent of taking a photograph by moving a single pixel sensor across the scene, but it allowed the Pioneers to capture the first close-up images of Jupiter and Saturn with minimal complexity. One of the most interesting aspects of the Pioneer missions was an unexpected scientific discovery known as the Pioneer Anomaly. Beginning in the 1980s, navigators tracking the spacecraft noticed a small but persistent discrepancy in their trajectories. Both Pioneer 10 and 11 appeared to be slowing down slightly more than could be explained by known forces like gravity and solar radiation pressure. This tiny deceleration, amounting to only about 8.74 times 10 to the negative 10 meters per second squared, was nonetheless clearly detectable over time. This anomaly led to decades of scientific debate. Some researchers proposed exotic explanations, suggesting that it might indicate a need to modify our understanding of gravity over large distances, or might even be evidence of dark matter. Others looked for more conventional explanations involving the spacecraft themselves. Finally, in 2012, an analysis using thermal modeling of the spacecraft determined that the anomaly could be fully explained by asymmetric thermal radiation. The heat radiating from the spacecraft's power systems was being emitted unevenly, producing a tiny but measurable thrust, like an extremely weak rocket. This seemingly mundane explanation nonetheless highlighted the extraordinary precision with which we can track spacecraft across billions of kilometers, where even the pressure of escaping heat becomes detectable. The Pioneer missions faced numerous challenges and experienced several notable incidents during their long journeys. Early in Pioneer 10's mission, the spacecraft's star sensor, used for navigation, became confused when it detected unexpected bright particles. These turned out to be fragments of the spacecraft's own thermal insulation that had broken loose and were reflecting sunlight as they drifted alongside. Engineers had to develop new procedures to distinguish these false stars from real navigation references. During Pioneer 11's closest approach to Jupiter, the radiation levels were so intense that the spacecraft's backup systems began to activate due to false commands generated by radiation-induced electronic noise. Fortunately, the primary systems continued to function correctly. These experiences provided valuable lessons for designing the radiation shielding of future spacecraft. As the Pioneers moved farther from the Sun, falling temperatures became a concern. The spacecraft were designed to operate in the cold environment of space, but their extremities, particularly the fuel lines for the thrusters, risked freezing. Engineers developed techniques to periodically pulse the thrusters to keep the fuel flowing and prevent it from freezing, a process that became part of routine operations for deep space missions. Both Pioneer spacecraft carried small amounts of radioactive plutonium not just for power generation, but also to heat critical components. This heating system, called radioisotope heater units, placed tiny amounts of plutonium-238 at strategic locations around the spacecraft. As this material naturally decayed, it released heat that kept nearby components within their operating temperature range, preventing electronic failures in the extreme cold of deep space. The trajectories of the Pioneer spacecraft were carefully calculated to accomplish their scientific goals while ensuring long-term stability. Pioneer 10's path after Jupiter would take it above the plane of the planetary orbits and toward the constellation Taurus. Pioneer 11, having visited both Jupiter and Saturn, was directed below the plane of the planetary orbits, providing a different perspective on the solar system and heading toward the constellation Aquila. These diverse paths were chosen in part to sample different regions of our solar neighborhood, maximizing the scientific return from the two spacecraft. The Pioneer missions created a wealth of new data about the environments they traversed. One significant discovery was the extent of Jupiter's enormous magnetosphere, the region of space dominated by the planet's magnetic field. Pioneer 10 found that this magnetosphere extends up to 7 million kilometers in the direction facing the Sun and stretches more than 700 million kilometers in the opposite direction, forming a magnetotail that extends beyond Saturn's orbit. Within this vast region, trapped charged particles create radiation belts thousands of times more intense than Earth's Van Allen belts. At Saturn, Pioneer 11 made discoveries about the planet's rings that would later be explored in more detail by the Voyagers. It found that what appeared from Earth as a few distinct rings was actually a complex system of thousands of narrow ringlets. It detected what appeared to be small shepherd moons whose gravity helps maintain the sharp edges of some rings. And it measured the thickness of the rings, finding that despite their enormous diameter of about 280,000 kilometers, they were perhaps as thin as 10 to 100 meters in some places, proportionally thinner than a sheet of paper. One of the most surprising findings came from the meteoroid detectors aboard both spacecraft. Scientists had expected to find significant amounts of dust and small particles in the outer solar system, but the Pioneers detected much less material than anticipated. This discovery suggested that the space between the planets is remarkably empty, with dust and debris being much rarer than previously thought. This information was valuable for planning future missions, indicating that spacecraft could travel through the outer solar system with minimal risk of damaging impacts. The Pioneer missions also provided new data about the boundaries of our solar system. As they traveled outward, their instruments measured how the influence of the Sun, in the form of solar wind and magnetic field, gradually diminishes. This information began to sketch the outline of the bubble that surrounds our solar system, called the heliosphere, though it would be left to later missions like Voyager to actually cross the boundary into interstellar space. Beyond their scientific achievements, the Pioneer spacecraft hold an important place in popular culture and the public imagination. The gold plaques they carry, with their enigmatic engravings of a nude man and woman, atomic and astronomical diagrams, and pulsar map, captured the public's imagination in a way that few aspects of space missions had before. These plaques represented something new in human history, a deliberate message created for unknown recipients in the distant future. They acknowledged the possibility that our spacecraft might someday be found by other technological civilizations, and they expressed a desire to communicate across the vast gulfs of time and space. Carl Sagan, who led the design of the plaques, recognized that they were as much symbolic as practical. The chance of another civilization finding either Pioneer spacecraft is infinitesimally small. The plaques were intended not only as an actual message to hypothetical extraterrestrials, but also as a message to humanity itself, a reminder that we are sending our creations on journeys that will outlast our civilization and possibly our species. The Pioneer plaques, and later the more elaborate Voyager golden records, invite us to think in cosmic timescales, to imagine a future where our spacecraft might be the only remaining evidence that humanity ever existed. The human figures on the plaques generated some controversy when they were first revealed. Some were uncomfortable with the nudity, simple and diagrammatic though it was. Others criticized the raised hand of the male figure as a gesture that might not be universally understood as peaceful. Still, others noted that the figures represented only a narrow slice of human physical diversity. These debates were valuable, highlighting the challenges inherent in creating a message intended to be universal, comprehensible across cultural and even biological divides. The scientific diagram on the plaque, showing the hyperfine transition of hydrogen, was a particularly clever inclusion. Hydrogen is the most abundant element in the universe, and this particular atomic transition produces radio emissions at a wavelength of 21 centimeters, a frequency well known to astronomers. This provides a universal unit of measurement that could be used by alien scientists to interpret the other dimensions shown on the plaque. The most complex element of the plaque is the pulsar map, showing the location of Earth relative to 14 pulsars, rapidly rotating neutron stars that emit precisely timed radio pulses. Each pulsar is indicated with a line showing the direction from our Sun, and its unique pulse frequency is noted in binary code. Since pulsars slow down at predictable rates, this information would allow a sufficiently advanced civilization to determine when the spacecraft was launched, even if it were found millions of years in the future. It's a celestial coordinate system, a cosmic address label for the home planet of the spacecraft's creators. As the years passed and the Pioneer spacecraft continued to function far beyond their designed lifespans, they took on an almost mythic quality. They became symbols of human ingenuity and perseverance, machines that kept operating in the face of incredible challenges, sending back whispers of data from regions no human had ever visited, not even with telescopes. Each communication from a Pioneer spacecraft represented a triumph, a tiny signal that had crossed an almost unimaginable distance to reach us. The final years of communication with the Pioneer spacecraft were both triumphant and poignant. As they moved farther from the Sun, the power available from their RTGs gradually diminished as the plutonium fuel continued its natural decay. Engineers had to make difficult decisions about which instruments to power down to conserve energy for the radio transmitter. System by system, the spacecraft's scientific capabilities were sacrificed to maintain the precious communication link with Earth. Despite these measures, the power continued to dwindle. The spacecraft grew colder as heaters were shut down to save electricity. Some components began to fail due to the extreme cold or the accumulated radiation damage from decades in space. The radio signals grew fainter, requiring longer and longer listening periods by the Deep Space Network to detect them. Finally, inevitably, the signals became too weak to detect at all. The last successful communication with Pioneer 10 was received on January 23, 2003, when the spacecraft was approximately 82 astronomical units from Earth, or about 12 billion kilometers. At that distance, a radio signal traveling at the speed of light takes over 11 hours to make the journey. Pioneer 11 fell silent earlier, with its last signals received on September 30, 1995. Even after contact was lost, NASA made periodic attempts to re-establish communication with Pioneer 10 for several more years, in case its radio transmitter had somehow recovered enough power to be detected. But these attempts were unsuccessful. The first emissaries humanity had sent to the outer planets had completed their missions and fallen silent, though they continue their physical journeys through the cosmos. Today, Pioneer 10 and 11 drift silently through space, having long since passed the boundary of our solar system. They carry no functioning instruments, no operating computers, no active communication systems. The plutonium in their power sources continues to decay, but with no systems to convert this heat to electricity, the spacecraft grow ever colder, approaching the background temperature of space itself, just a few degrees above absolute zero. Yet in their silence and stillness, the Pioneer spacecraft have achieved a kind of immortality. Barring an extremely unlikely collision with another object, they will continue their journeys indefinitely, becoming humanity's first interstellar travelers. Pioneer 10 is heading roughly toward the star Aldebaran and will pass in its vicinity in about 2 million years. Pioneer 11 is moving toward the constellation Aquila and will pass near the star Lambda Aquila in roughly 4 million years. On these timescales, almost unimaginable to human consciousness, the Earth itself will have changed dramatically. Continental drift will have reshaped our planet's surface. Ice ages will have come and gone. Human civilization as we know it will almost certainly have either disappeared or transformed into something unrecognizable to us today. Yet the Pioneer spacecraft will remain, perhaps the longest-lasting artifacts our civilization will ever create, still carrying their golden messages to the stars. In many ways, the Pioneer missions represent a golden age of space exploration, a time when humanity first reached beyond the confines of the inner solar system and touched the outer planets. They were missions of pure discovery, driven not by military or commercial interests, but by scientific curiosity and the human desire to explore the unknown. The data they returned transformed our understanding of the solar system and laid the foundation for all subsequent missions to the outer planets. The engineering achievements of the Pioneer program influenced the design of many later spacecraft. The spin stabilization technique, pioneered by these missions, was adopted for many subsequent deep space probes. The radioisotope power systems proved their worth for long-duration missions beyond the reach of effective solar power. The communication techniques developed to detect and interpret the faint radio signals from these distant spacecraft became standard practices for deep space missions. Perhaps most importantly, the Pioneer missions demonstrated that the seemingly insurmountable challenges of deep space exploration could be overcome with ingenuity, careful planning, and a certain amount of audacity. They showed that human-made objects could survive the asteroid belt, withstand the intense radiation of Jupiter, and function for decades in the harsh environment of space. They proved that we could communicate across billions of kilometers and precisely navigate spacecraft on trajectories that would carry them to specific locations around planets over 400 million kilometers from Earth. In doing so, the Pioneer spacecraft opened the door to all subsequent exploration of the outer solar system. The Voyagers, Galileo, Cassini, New Horizons, Juno, all these missions and more trace their lineage back to the Pioneers, the true pathfinders of deep space exploration. As we continue to explore our solar system and dream of someday sending probes to other stars, we build upon the legacy of Pioneer 10 and 11. These remarkable spacecraft, designed and built with 1970s technology, launched when computers filled entire rooms and before digital cameras existed, nonetheless accomplish feats that still inspire awe today. They remind us of what can be achieved when human creativity and determination are focused on expanding the boundaries of knowledge and exploration. In their continuing silent journeys through interstellar space, carrying their gold plaques with messages from a civilization that reached for the stars, the Pioneer spacecraft have become more than mere machines. They are symbols of human aspiration, embodiments of our curiosity about the cosmos and our place within it. Long after their electronic hearts have stopped beating, They continue their mission as ambassadors of Earth, bearing witness to humanity's first tentative steps into the vast ocean of interstellar space. The human desire to explore does not diminish with distance or difficulty. If anything, the most remote, challenging frontiers call to us with the greatest allure. For decades after the Voyager missions revealed the wonders of the giant planets, one major world in our solar system remained unvisited, unseen, except as a distant, blurry point of light. Pluto, orbiting in the dim twilight at the edge of our planetary system, awaited its first explorer. This is the story of New Horizons, humanity's first mission to Pluto and the mysterious region beyond, known as the Kuiper Belt. It is a tale of persistence, ingenuity, and discovery, of a small spacecraft that journeyed farther to explore a new world than any mission before it, and of the patient team of scientists and engineers who made this remarkable achievement possible. The story of New Horizons begins not with its launch, but with a long campaign by planetary scientists to convince NASA and the American government to fund a mission to Pluto. As early as 1989, with the Voyager 2 flyby of Neptune still fresh in memory, scientists began proposing missions to the only then recognized planet that had not been visited by a spacecraft. These early concepts included a Pluto fast flyby and later a Pluto Kuiper Express, but budget constraints led to the cancellation of these missions before they progressed beyond the planning stage. The scientific case for exploring Pluto was compelling. Observations from Earth had revealed that this distant world possessed a thin atmosphere of nitrogen, methane, and carbon monoxide that would expand and contract dramatically as Pluto moved through its highly elliptical orbit, potentially freezing out entirely onto the surface during the long, cold Plutonian winter. Spectroscopic studies indicated that its surface contained exotic ices unlike anything found on other planets. And the discovery in 1978 of Pluto's largest moon, Charon, suggested a complex system worthy of closer study. Moreover, Pluto represented an entirely new class of world. Neither a terrestrial planet like Earth, nor a gas giant like Jupiter, it appeared to be the largest known member of a third category, the ice dwarfs, small worlds composed largely of frozen compounds that orbit in the outer reaches of our solar system. Visiting Pluto would expand our understanding of planetary diversity and the processes that shaped different regions of the solar system. The scientific urgency to reach Pluto increased in the 1990s, with two significant developments. First, ground-based observations revealed that Pluto's thin atmosphere was gradually expanding as the planet moved toward the portion of its orbit where it would be nearest to the Sun, a state that occurs only once every 248 years. Scientists feared that if a mission did not reach Pluto before it began to move away from the Sun again, the atmosphere would begin to freeze out onto the surface, making it impossible to study in its expanded state. Second, in 1992, astronomers discovered the first object in what would come to be known as the Kuiper Belt, a vast ring of icy bodies orbiting beyond Neptune. This discovery transformed our understanding of the outer solar system, revealing that Pluto was not an isolated oddity, but the largest known member of a vast population of objects. The Kuiper Belt suddenly emerged as an entirely unexplored region of our solar system, a fossil remnant of the planetary formation process that could provide crucial insights into the early history of our cosmic neighborhood. These developments lent new urgency to the scientific community's push for a Pluto mission. In 2000, the National Academy of Sciences placed high priority on a Pluto Kuiper Belt mission in its influential Decadal Survey of Planetary Science, a document that guides NASA's mission planning. This endorsement, combined with a grassroots campaign by planetary scientists and space enthusiasts, finally led NASA to issue a call for mission proposals in late 2000. The winning proposal came from a team led by planetary scientist Alan Stern of the Southwest Research Institute. Their mission, named New Horizons, would be designed to reach Pluto in a reasonable time frame while carrying a suite of instruments capable of studying not only Pluto and its moons, but also one or more Kuiper Belt objects beyond. The mission was approved in 2001, with a target launch date of January 2006. The design of the New Horizons spacecraft reflected both the enormous challenges of reaching Pluto and the need to do so with a limited budget. The entire spacecraft weighs just 478 kilograms, about the size of a grand piano, making it remarkably light for a vessel capable of traveling to the edge of the solar system. Its compact design was necessitated by the need for the highest possible launch velocity to reach Pluto, over 5.5 billion kilometers away, within a reasonable time frame. Like the Pioneer and Voyager spacecraft before it, New Horizons is powered by a radioisotope thermoelectric generator, which converts the heat from decaying plutonium-238 into electricity. This power source is essential for missions to the outer solar system, where sunlight is too faint for solar panels to generate sufficient power. At Pluto, sunlight is 1,600 times weaker than at Earth, rendering solar power impractical for a mission requiring significant electrical capacity for its scientific instruments and communications. The spacecraft carries 7 scientific instruments, each designed to reveal different aspects of the Plutonian system. The Long-Range Reconnaissance Imager, or LORRI, is a high-resolution camera capable of resolving features as small as 100 meters across on Pluto's surface from a distance of 12,000 kilometers. The RALPH instrument combines a color camera with an imaging spectrometer to map the composition of surface materials. ALICE, an ultraviolet spectrometer, would study Pluto's atmosphere. REX, the radio science experiment, would measure atmospheric pressure and temperature. SWAP and PEPSI would study the escape of Pluto's atmosphere into space and its interaction with the solar wind. And the Student Dust Counter, built and operated by students at the University of Colorado, would measure the tiny particles of dust that New Horizons encountered on its journey. To conserve power during the long cruise to Pluto, much of New Horizons' journey would be spent in hibernation, with most systems powered down and only essential functions operating. The spacecraft would wake up for annual systems checks and course corrections, then return to its electronic slumber. This approach not only saved power, but also reduced wear on the spacecraft's systems, helping to ensure they would still be operational when New Horizons finally reached its destination after a journey of nearly a decade. The mission faced a dramatic setback in December 2005, just weeks before the scheduled launch, when a storm damaged the spacecraft during preparations at Cape Canaveral. Repairs were quickly made, but this delay, combined with additional technical issues with the Atlas V rocket that would launch New Horizons, pushed the launch to the very end of the viable launch window. Had these issues delayed the mission by more than a few weeks, the entire mission would have been postponed by more than a year, potentially missing the optimal arrival time at Pluto. Fortunately, New Horizons successfully launched on January 19, 2006, beginning its long journey to the edge of the solar system. The Atlas V rocket, augmented with 5 solid rocket boosters and a powerful upper stage, sent the spacecraft directly into an Earth escape trajectory at the incredible speed of 16.26 kilometers per second, the fastest launch velocity ever achieved by a human-made object. This speed was necessary to reach Pluto within a reasonable time frame, but even at this pace, the journey would take over 9 years. To further increase its velocity, New Horizons was directed toward Jupiter for a gravity assist maneuver. The spacecraft passed Jupiter on February 28, 2007, just 13 months after launch. This close flyby bent New Horizons' trajectory and increased its speed by approximately 4 kilometers per second, shaving years off the journey to Pluto. The Jupiter encounter served as more than just a navigational aid. It provided an opportunity to test and calibrate the spacecraft's instruments on a known target before the Pluto flyby. New Horizons captured detailed images of Jupiter's dynamic cloud patterns, studied its moons, and observed a volcanic eruption on Io in real time. These observations not only provided valuable science but also gave the mission team confidence in the performance of the spacecraft's systems and instruments. After the Jupiter flyby, New Horizons settled in for the long cruise to Pluto. The spacecraft spent much of this time in hibernation mode, with most systems powered down to reduce wear and conserve energy. Periodically, the spacecraft would be awakened for systems checks and course corrections, then return to its electronic slumber. Like a marathon runner conserving strength for the final sprint, New Horizons quietly continued its journey through the outer solar system, crossing the orbits of Saturn, Uranus, and Neptune, though at points in space far from the planets themselves. As New Horizons drew closer to Pluto, the team faced a significant challenge. Despite being discovered in 1930 by astronomer Clyde Tombaugh, Pluto's orbit was not known with sufficient precision to guarantee that the spacecraft would pass through the optimal point for observations. Furthermore, The discovery of additional moons around Pluto, beyond Charon, raised concerns about the potential for hazardous debris in the Pluto system that could damage or destroy the spacecraft if it passed through at high velocity. To address these challenges, the mission team began an intensive observation campaign in 2011, using both ground-based telescopes and the Hubble Space Telescope to refine knowledge of Pluto's position and search for potential hazards in its vicinity. By 2014, these observations had led to the discovery of 2 additional small moons, Kerberos and Styx, bringing the total number of known Plutonian moons to 5. More importantly, they allowed the team to calculate Pluto's position with much greater accuracy and to identify a safe trajectory through the system. On December 6, 2014, after nearly 9 years of mostly silent cruising, New Horizons was awakened from its final hibernation period. The spacecraft was now less than 200 million kilometers from Pluto, close enough that its cameras could begin to resolve the dwarf planet as more than just a point of light. Over the following months, as New Horizons drew closer, Pluto gradually transformed from a distant, mysterious dot into a real world with visible surface features. By April 2015, the images from New Horizons were already surpassing the best views of Pluto ever obtained from Earth or the Hubble Space Telescope. Bright and dark patches became visible on the surface, hinting at the complex terrain that would soon be revealed in greater detail. The spacecraft's instruments also began to collect data on Pluto's atmosphere and its interaction with the solar wind. As New Horizons approached its target, a potential disaster struck. On July 4, 2015, just 10 days before the scheduled closest approach to Pluto, contact with the spacecraft was unexpectedly lost. For a tense hour and 21 minutes, the mission team was unable to communicate with New Horizons. Had a critical system failed at this crucial moment? Had the spacecraft been struck by a particle of debris? The decades of work and nearly $700 million investment in the mission seemed suddenly at risk. To the immense relief of the mission team, contact was eventually re-established. Analysis revealed that the spacecraft's primary computer had become overloaded while simultaneously processing new command sequences and compressing scientific data. The computer had automatically reset itself and entered safe mode, temporarily halting science operations. Within 3 days, the team had recovered the spacecraft and returned it to normal operations, with minimal impact on the science plan for the Pluto flyby. As New Horizons closed in on Pluto, the pace of discoveries accelerated dramatically. The spacecraft revealed that Pluto is slightly larger than previously thought, with a diameter of 2,377 kilometers, definitively establishing it as the largest known object in the Kuiper Belt. Images showed a surprisingly diverse surface, with some regions appearing relatively smooth and others highly textured. Most strikingly, a large, bright, heart-shaped feature appeared on one hemisphere, immediately capturing public attention and becoming the most iconic image of the encounter. On July 14, 2015, New Horizons made its closest approach to Pluto, passing just 12,500 kilometers above the surface at a velocity of over 14 kilometers per second. The entire flyby was automated, with the spacecraft executing a precisely choreographed sequence of observations using all 7 of its scientific instruments. So distant was Pluto that radio signals from Earth took 4.5 hours to reach the spacecraft, making real-time control impossible. The mission team could only wait anxiously as New Horizons silently conducted its exploration, unable to know whether the flyby was proceeding as planned until well after the closest approach had occurred. Adding to the tension, New Horizons was out of communication with Earth during the closest approach, as it was fully occupied with gathering scientific data. Not until almost 22 hours after closest approach did the spacecraft reorient itself to point its antenna toward Earth and transmit a status signal, confirming that it had successfully completed its primary mission. The mission operations manager, Alice Bowman, announced to the world, "We have a healthy spacecraft. We have recorded data from the Pluto system, and we are outbound from Pluto." Cheers erupted from the mission team and space enthusiasts around the world. The data gathered during the flyby would take more than 16 months to transmit back to Earth, due to the immense distance and the limited transmission power available to the spacecraft. But the initial images and information that arrived in the days and weeks following the encounter revealed a world far more complex and dynamic than anyone had anticipated. Pluto's surface displayed an astonishing variety of terrains. The western lobe of the heart-shaped region, informally named Sputnik Planitia, proved to be a vast plain of nitrogen ice. This region showed no impact craters, indicating that the surface is geologically young, perhaps less than 10 million years old. Even more surprisingly, detailed images revealed evidence of flowing glaciers and polygonal patterns in the ice that suggested ongoing convection, with warmer ice rising from below and cooler ice sinking, a sign that Pluto's interior still retains significant heat. In stark contrast to the smooth ice plains, other regions of Pluto displayed rugged mountains of water ice, some rising as high as 3 to 4 kilometers above the surrounding terrain. These mountains, which the team informally named after pioneering explorers and mountaineers from Earth, such as Hillary and Tenzing Montes, are comparable in height to the Rocky Mountains but are composed primarily of water ice, which at Pluto's surface temperature of minus 230 degrees Celsius behaves more like rock than like the ice we know on Earth. Perhaps the most unexpected feature was a region of dark, reddish material centered around Pluto's equator. This coloration is thought to result from complex organic compounds called tholins, created when methane in Pluto's atmosphere is broken down by ultraviolet radiation from the distant sun and recombines into more complex molecules that then settle onto the surface. This process links Pluto to Titan, Saturn's largest moon, where similar chemistry occurs. The observations also revealed surprising atmospheric phenomena. Pluto's atmosphere, though thin, extends much higher above the surface than expected, reaching to an altitude of 1,600 kilometers. Layers of haze were visible, created as methane and other gases condense at different altitudes. Most dramatically, backscattered sunlight revealed that the atmosphere forms a complete ring around Pluto, even on the night side, indicating that it is globally distributed rather than concentrated on the warmer, sunlit hemisphere, as some models had predicted. New Horizons also provided detailed observations of Pluto's moons. Charon, the largest, proved to be a world worthy of extensive study in its own right. With a diameter of 1,212 kilometers, about half that of Pluto, Charon is proportionally the largest moon relative to its parent body in the solar system. Unlike Pluto, Charon displays no evidence of a substantial atmosphere. Its surface features include extensive tectonic structures, suggesting that the moon's crust fractured as an internal ocean froze and expanded, and a darkened North Polar region, informally named Mordor Macula, thought to consist of material captured from Pluto's atmosphere. The four smaller moons, Nix, Hydra, Kerberos, and Styx, were revealed to be irregularly shaped, rapidly rotating bodies ranging from 47 kilometers in their longest dimension for Nix, down to just 16 kilometers for Styx. These tiny moons tumble chaotically as they orbit, their rotation influenced by the complicated gravitational interplay between Pluto and Charon. One of the most profound revelations from the New Horizons mission was that Pluto, despite its small size and extreme distance from the Sun, is a geologically active world. The absence of impact craters in some regions indicates recent resurfacing, and the evidence of flowing glaciers suggests ongoing geological processes. This activity requires an internal heat source, likely the decay of radioactive elements in Pluto's core, combined with the insulating properties of its icy crust. This finding challenged prevailing assumptions about small, icy worlds at the edge of the solar system. Before New Horizons, many scientists had expected Pluto to be a relatively static, heavily cratered body, its geological evolution largely complete billions of years ago. Instead, it appears to be a dynamic world, with ongoing physical and chemical processes reshaping its surface even today. This discovery has profound implications for our understanding of heat retention and geological activity in small planetary bodies throughout the universe. As the data continued to stream back to Earth over the following months, the complexity of the Pluto system only became more apparent. Analyses of the composition of different regions revealed a diverse chemical landscape. The Bright Heart region consists primarily of nitrogen ice, mixed with carbon monoxide and methane, while other areas show concentrations of water ice, methane ice, or complex organic compounds. This diversity indicates a history of geological and atmospheric processes sorting and depositing different materials across the surface. The mission also provided insights into the formation and evolution of the Pluto-Charon system. The similar densities of the two bodies and their mutual orbit around a point outside of Pluto's surface strongly suggest that they formed from a giant impact, similar to the event thought to have created Earth's moon. In this scenario, a large body struck Proto-Pluto, ejecting material that subsequently coalesced to form Charon. This shared origin explains why Charon's composition is similar to Pluto's, primarily water ice with some ammonia compounds, rather than the nitrogen ice that covers much of Pluto's surface. Beyond the scientific insights, the New Horizons mission captivated public imagination in a way that few recent space missions had achieved. The transformation of Pluto from a distant, mysterious point of light into a complex, beautiful world with landscapes that seem almost familiar, despite their exotic composition, resonated with people around the globe. The heart-shaped feature, officially named Tombor Regio after Pluto's discoverer, became an instant cultural icon, appearing on T-shirts, posters, and social media. The mission also gained poignancy from its timing. Just 9 years before New Horizons arrived at Pluto, the International Astronomical Union had controversially reclassified Pluto from a planet to a dwarf planet, a decision that generated significant public backlash. Many who had grown up learning about 9 planets felt that something had been taken away. The New Horizons flyby, revealing Pluto's complexity and beauty, seemed to restore some of its dignity regardless of its official classification. As mission leader Alan Stern frequently noted, Pluto was demoted because of its small size, but its geology is anything but small. It's a real planet, as complex and interesting as any we've explored. Even as the team continued to analyze the wealth of data from Pluto, New Horizons was already speeding toward its next destination. The mission had been designed from the beginning as not just a Pluto reconnaissance, but as an exploration of the Kuiper Belt, the vast ring of icy bodies beyond Neptune's orbit. Following the Pluto flyby, the team used the Hubble Space Telescope to identify potential targets within reach of the spacecraft's remaining fuel. In August 2015, they selected an object then known only as 2014 MU69, located about 1.6 billion kilometers beyond Pluto. Ground-based observations suggested it was about 45 kilometers in diameter, but little else was known about it. The team executed a series of 4 trajectory correction maneuvers in October and November 2015, using precious fuel to redirect New Horizons toward this distant target. As the spacecraft journeyed onward, its destination was given the official designation 486958 by the Minor Planet Center and the nickname Ultima Thule by the New Horizons team, referencing a classical term for a place beyond the known world. Later, after criticism that this name had been appropriated by Nazi occultists in the 20th century, the team adopted the name Arrokoth, a Native American term meaning sky in the Powhatan language. The journey to Arrokoth would take more than 3 years, during which the spacecraft would travel an additional 1.6 billion kilometers through the void. Unlike the cruise to Pluto, which included long periods of hibernation, New Horizons remained active during this extended mission, conducting distant observations of more than 24 other Kuiper Belt objects and studying the environment of this little explored region. One of the most significant findings from these cruise observations was that the Kuiper Belt contains far less dust than expected. The Student Dust Counter instrument, which had been measuring tiny particles throughout the journey, detected fewer impacts than models had predicted. This suggests that collisions between Kuiper Belt objects occur less frequently than thought, possibly because the population of small bodies is lower than current theories indicate. This finding has important implications for understanding the evolution of the outer solar system and the processes that shaped the orbits and compositions of trans-Neptunian objects. As New Horizons approached Arrokoth, the challenges facing the mission team were even greater than during the Pluto encounter. The target was much smaller, making it difficult to detect until the spacecraft was relatively close. It was also much more distant, meaning that communications took longer, and the light available for imaging was even fainter. And the team had far less preparation time, as the target had only been discovered after New Horizons launched, unlike Pluto, which had been studied for decades. Despite these challenges, the mission team developed an observation plan to maximize the scientific return from the encounter. As with the Pluto flyby, The closest approach would be fully automated, with the spacecraft executing a pre-programmed sequence of observations. Given the extreme distance, the data rate for transmitting information back to Earth was painfully slow, just 1,000 bits per second, less than 1/1000th, the speed of an early 1990s dial-up modem. At this rate, it would take about 20 months to send back all the data collected during the flyby. On January 1st, 2019, at 5:33 Universal Time, New Horizons made its closest approach to Arrokoth, passing just 3,500 kilometers from its surface. At a distance of 6.5 billion kilometers from Earth, this was by far the most distant planetary encounter in human history. The radio signal confirming the successful flyby took 6 hours and 8 minutes to reach Earth, where it was received by NASA's Deep Space Network antenna in Madrid, Spain. The first low-resolution images returned after the flyby revealed a remarkably unusual object. Far from being a simple, roughly spherical body like most asteroids, Arrokoth consists of two distinct lobes, connected by a narrow neck, resembling a snowman or a peanut. This binary structure, technically known as a contact binary, suggests that Arrokoth formed from two separate objects that gently came together in the distant past. As higher resolution images were transmitted back to Earth over the following weeks, this extraordinary structure became clearer. The two lobes, nicknamed Ultima and Tula by the team, are roughly 14 kilometers and 8 kilometers across, respectively. They appear to be aligned along their poles, suggesting that they approached each other very slowly and gradually, rather than colliding violently. This alignment provides valuable constraints on models of how planetesimals, the building blocks of planets, formed in the early solar system. The surface of Arrokoth appears remarkably uniform and red in color, similar to many other trans-Neptunian objects. It shows no evidence of impact craters at the resolution available to New Horizons, suggesting that the surface is relatively young or that impacts are rare in this distant region of the solar system. The red coloration likely results from organic compounds created by the irradiation of ices by cosmic rays and distant sunlight over billions of years. Perhaps most significantly, the structure and composition of Arrokoth provides strong support for a model of planetesimal formation known as the streaming instability. In this model, small particles in the solar nebula, the cloud of gas and dust from which the solar system formed, gradually cluster together due to aerodynamic effects until they become dense enough to collapse under their own gravity. This gentle process better explains Arrokoth's binary structure than alternative models involving more violent collisions. This insight into planetesimal formation represents a major scientific achievement of the New Horizons extended mission. By studying an object that has remained largely unchanged since the birth of the solar system, the mission has provided a window into the processes that created the planets, including Earth. Arrokoth can be thought of as a fossil from the solar system's infancy, preserving evidence of formation mechanisms that operated 4.5 billion years ago, but have since been erased elsewhere by subsequent geological evolution. As of today, New Horizons continues its journey through the Kuiper Belt, with enough power to operate until the mid-2030s and enough propellant for one more significant course correction. The team hopes to identify another Kuiper Belt object within reach for a potential third flyby, though finding a suitable target within the fuel constraints is challenging. Even without another close flyby, the spacecraft will continue to study distant Kuiper Belt objects and measure the properties of the interstellar medium as it gradually approaches the edge of the solar system. Regardless of what discoveries may yet lie ahead, the New Horizons mission has already transformed our understanding of the outer solar system. Before this mission, Pluto was little more than a distant point of light. Its nature and history largely matters of speculation. The Kuiper Belt was a relatively recent discovery, its role in the solar system's history still being defined. Today, thanks to New Horizons, we have detailed maps of Pluto's surface, knowledge of its complex geology and atmosphere, insights into the structure and evolution of the Pluto-Charon system, and a close-up view of a primitive Kuiper Belt object that has illuminated the very formation of our solar system. The mission represents a triumph of human curiosity, ingenuity, and perseverance. From the decades-long campaign to secure approval and funding, through the complex design and construction process, to the 9-year journey across more than 5 billion kilometers of space, and finally, to the breathtaking discoveries that continue to emerge from the data, New Horizons exemplifies the extraordinary achievements possible when human beings direct their collective efforts toward exploring the unknown. As New Horizons recedes ever farther from Earth, it carries with it a lasting legacy. Like the Pioneer and Voyager spacecraft before it, it bears human artifacts into the cosmos. Mounted on the spacecraft is a small container holding some of the ashes of Clyde Tombaugh, Pluto's discoverer, who passed away in 1997. Also aboard are 2 United States flags, a fragment of Spaceship One, the first privately funded human spacecraft, and a Maryland State Quarter, the home state of the Johns Hopkins Applied Physics Laboratory, where New Horizons was built. Perhaps most poignantly, it carries a compact disc containing the names of more than 434,000 people who signed up to send their names to Pluto. These physical mementos pale in significance, however, beside the scientific and cultural impact of the mission. New Horizons has expanded the frontier of human knowledge, revealing worlds that were once beyond our perception and providing insights into the processes that shaped our own planet and the solar system we inhabit. It has inspired a new generation of explorers and scientists, demonstrating that even in the 21st century, there remain profound discoveries to be made in our cosmic neighborhood. As we reflect on the journey of New Horizons, we might recall the words of the mission plaque, which reads in part, "The New Horizons mission is the first reconnaissance of Pluto and the Kuiper Belt, ancient worlds on the outskirts of our solar system." Launched from Cape Canaveral on January 19, 2006, this spacecraft traveled farther and faster than any before to provide the first up-close images and science data from these distant planetary bodies, helping us to understand worlds at the edge of our solar system. These words embody the spirit of exploration that drives missions like New Horizons, the desire to see what lies beyond the horizon, to understand the unknown, to expand the boundaries of human knowledge. As New Horizons continues its silent journey into the cosmic ocean, it carries with it not just scientific instruments and human artifacts, but the embodiment of this exploratory spirit, a testament to humanity's enduring curiosity about the universe we inhabit. The legacy of New Horizons extends beyond its scientific achievements to its influence on future missions and exploration strategies. The proven ability to design, build, and operate a spacecraft capable of functioning reliably after a journey of nearly a decade and across billions of kilometers has important implications for future deep space missions. The successful use of hibernation modes to conserve power and reduce wear on systems, the effective operation in regions where solar power is impractical, and the ability to precisely navigate to targets whose positions are not perfectly known, all represent valuable engineering achievements that will inform the design of future missions to the outer solar system and beyond. The discoveries at Pluto have also raised new questions that future missions will seek to answer. The evidence of geological activity raises questions about the internal heat sources in small, distant worlds and the potential for subsurface oceans similar to those believed to exist within Europa, Enceladus, and other icy moons. The complex chemistry observed in Pluto's atmosphere and on its surface suggests processes that may have relevance to the development of organic compounds throughout the solar system. And the unexpectedly diverse terrain on both Pluto and Charon indicate that our models of how small planetary bodies evolve over time need significant revision. These questions have already influenced proposals for future missions, including concepts for Pluto orbiters or landers that could study the dwarf planet in much greater detail than was possible during New Horizons' brief flyby. While such missions would be challenging, requiring significant advances in propulsion technology to reach Pluto in a reasonable timeframe, the scientific case for a return to this fascinating world has been strengthened enormously by New Horizons' revelations. Beyond the scientific and engineering impacts, New Horizons has also influenced how we communicate and share the adventure of space exploration. The mission unfolded in the era of social media, allowing the public to follow the journey and discoveries in real time in ways that weren't possible for earlier missions to the outer planets. Images and findings were shared globally within hours of their reception on Earth, creating a sense of collective participation in the exploration process. The mission team embraced this connectivity, engaging the public through online platforms, live events, and educational initiatives. They invited people to submit names to be carried on the spacecraft, to vote on features to be imaged during the Pluto flyby, and to suggest names for the newly discovered surface features. This approach helped to build a global community of support for the mission and for planetary exploration more broadly. The images from New Horizons, particularly the now iconic heart-shaped feature on Pluto, have become part of our shared cultural imagery of the solar system. Just as the Voyager images of Jupiter's Great Red Spot or Saturn's rings entered popular consciousness in previous decades, the heart of Pluto has become a recognizable symbol of the beauty and wonder to be found even at the farthest reaches of our planetary neighborhood. As New Horizons continues its journey, now more than 7 billion kilometers from Earth and still functioning well, it joins an elite group of spacecraft that have ventured into the realm beyond the traditional planets. Along with the Pioneers and Voyagers, it represents humanity's first physical presence in the vast outer regions of our solar system, a region that contains countless objects and may hold important clues to the formation and evolution of our planetary system. In the coming decades, as power gradually diminishes and contact eventually ceases, New Horizons, like its predecessors, will continue a silent journey that will ultimately take it into interstellar space. Though it lacks the formal messages to extraterrestrial civilizations carried by the Pioneers and Voyagers, it nonetheless serves as an ambassador of human curiosity and technological achievement, a physical embodiment of our species' desire to explore and understand the cosmos. Perhaps the most profound legacy of New Horizons is how it has expanded our mental map of the solar system. Before this mission, the outer solar system beyond Neptune remained largely abstract in the public imagination, a distant, cold realm of dim points of light. After New Horizons, we can visualize the mountains and plains of Pluto, the reddish hue of Arrokoth, the complex interactions of atmospheres and surfaces in these distant worlds. What was once remote and conceptual has become tangible and concrete, expanding the territory we can mentally inhabit. In this way, New Horizons continues the grand tradition of exploration that has defined human history, pushing back the frontier of the unknown and expanding the realm of human experience. From the early navigators who first ventured beyond the sight of land, to the pioneers who crossed continents, to the astronauts who first left Earth, the impulse to explore the unknown seems deeply ingrained in human nature. New Horizons represents the extension of this impulse to the very edge of our solar system, a robot explorer carrying human curiosity to realms we cannot physically reach. As we contemplated, the images returned from the edge of the solar system, showing worlds formed in the same primordial cloud as Earth, but following vastly different evolutionary paths. We gain perspective on our own world and its place in the cosmos. We are reminded of the remarkable diversity of environments within our solar system, the complex processes that have shaped the planets and smaller bodies, and the delicate balance of conditions that have made Earth hospitable to life as we know it. This perspective is perhaps the ultimate gift of missions like New Horizons, a reminder of both the uniqueness of our home planet and its connection to a larger cosmic context. In the heart-shaped plane of Pluto's surface, in the gentle binary embrace of Arrokoth's two lobes, in the patterns of methane frost on mountain ridges 14,000 times more distant than our moon, we find not only scientific data, but also a kind of cosmic poetry, an invitation to wonder at the beauty and complexity of a universe that continues to surprise and inspire us. In the vast darkness beyond the planets lies a frontier that marks the boundary between our solar neighborhood and the greater galaxy. This region, where the influence of our sun begins to give way to the interstellar medium, is not a sharp line but a complex, layered transition zone that has captivated scientists since the dawn of the space age. Here, at the edge of the solar system, our most distant spacecraft have made discoveries that have transformed our understanding of our cosmic home and its relationship to the interstellar environment beyond. The concept of the solar system having an edge or boundary emerged in the 1950s as scientists began to understand the solar wind, the constant stream of charged particles flowing outward from the sun in all directions. Eugene Parker, who first theoretically described this phenomenon in 1958, recognized that this flow of particles must eventually encounter the thin gas and dust that fills the space between stars, creating some form of boundary or transition region. For decades, this boundary remained theoretical, beyond the reach of direct observation. Scientists developed models and made predictions, but the actual structure and characteristics of this distant region could only be inferred from limited data. It wasn't until our most far-reaching spacecraft, particularly the Voyagers, reached sufficient distance from the Sun that we began to gather direct evidence about the nature of this mysterious frontier. To understand the edge of the solar system, we must first understand the heliosphere, the vast bubble of space dominated by the Sun's influence. The heliosphere is created and maintained by the solar wind, which flows outward from the Sun at speeds between 300 and 700 kilometers per second. This supersonic stream of charged particles, primarily electrons and protons, carries with it the Sun's magnetic field, creating what scientists call the interplanetary magnetic field. As the solar wind travels outward, it pushes against the interstellar medium, the diffuse gas and dust that fills the space between stars. This interstellar material, though incredibly tenuous by earthly standards, with just a few atoms or molecules per cubic centimeter, exerts its own pressure and carries its own magnetic field. The interaction between these two regions, the heliosphere created by the Sun and the interstellar medium beyond, forms the complex boundary at the edge of our solar system. This boundary is not a single sharp line, but a series of transition zones. Moving outward from the Sun, a spacecraft would first encounter a region called the termination shock. Here, the solar wind, which has been traveling at supersonic speeds since leaving the Sun, suddenly slows to subsonic speeds as it begins to feel the pressure of the interstellar medium ahead. This abrupt deceleration creates a shock wave, similar in principle to the sonic boom created by a supersonic aircraft. Beyond the termination shock lies the heliosheath, a turbulent region where the slowed solar wind becomes compressed and turbulent as it continues to push against the interstellar medium. The physics of this region is complex, with magnetic fields becoming twisted and contorted, creating bubbles and filaments of plasma, the electrically charged gas that makes up the solar wind. Finally, at the outermost edge of the heliosphere lies the heliopause, the true boundary between the solar system and interstellar space. Here, the outward pressure of the solar wind balances against the inward pressure of the interstellar medium. Beyond this point, the influence of the interstellar medium becomes dominant, though some effects of the Sun's gravity and radiation continue much farther. Some models suggest additional features beyond the heliopause, such as a bow shock or bow wave, where the entire heliosphere, moving through the interstellar medium as the Sun orbits the center of the galaxy, creates a disturbance in the surrounding interstellar gas. The current evidence suggests that our Sun may be moving too slowly relative to the local interstellar medium to create a true bow shock, but it likely does produce a more gentle bow wave. For most of the space age, our understanding of these regions remained theoretical. But beginning in the 1990s, our most distant emissaries began to approach this mysterious boundary, offering the first direct observations of the edge of the solar system. Voyager 1, launched in 1977, became the first spacecraft to cross the termination shock in December 2004, at a distance of approximately 94 astronomical units from the Sun. An astronomical unit, or AU, is the average distance between Earth and the Sun, about 150 million kilometers, making the termination shock about 14 billion kilometers from the Sun. Voyager 2 followed, crossing the termination shock in August 2007 at a distance of about 84 astronomical units, approaching from a different direction. The difference in where the two spacecraft encountered the termination shock, with Voyager 2 crossing it closer to the Sun than Voyager 1, provided an important insight. The heliosphere is not perfectly spherical, but is compressed on one side and elongated on the other, shaped by the motion of the Sun through the interstellar medium and by the influence of the interstellar magnetic field. This asymmetry continues to be studied and has important implications for how our solar system interacts with its galactic environment. After crossing the termination shock, both Voyager spacecraft entered the heliosheath, that turbulent region between the termination shock and the heliopause. Here, they made a series of surprising discoveries that challenged existing models of the outer heliosphere. The solar wind in this region proved to be more variable and structured than expected, with distinct bubbles or cells of plasma separated by boundaries, where the magnetic field orientation changed abruptly. The Voyagers also detected an unexpected slowing of the solar wind speed as they traveled through the heliosheath. Rather than maintaining a relatively consistent velocity after the initial deceleration at the termination shock, the solar wind continued to slow, eventually reaching speeds of less than 50 kilometers per second, much lower than models had predicted. This observation suggested that energy was being transferred from the solar wind to other forms, possibly heating the plasma or accelerating charged particles. Another surprise came in the form of anomalous cosmic rays, high-energy charged particles that were thought to be accelerated at the termination shock. The Voyagers found that the intensity of these particles continued to increase well into the heliosheath, suggesting that they were being accelerated throughout this region rather than primarily at the shock boundary. This discovery required a revision of models of particle acceleration in the outer heliosphere. After several years traversing the heliosheath, Voyager 1 reached another significant milestone. On August 25, 2012, at a distance of 121 astronomical units from the Sun, the spacecraft detected a dramatic change in its environment. The number of charged particles originating from the Sun suddenly dropped to nearly zero, while the number of galactic cosmic rays, high-energy particles from elsewhere in the galaxy, sharply increased. Magnetic field measurements also showed a significant change in strength and direction. These observations provided compelling evidence that Voyager 1 had crossed the heliopause and entered interstellar space, becoming the first human-made object to leave the solar bubble and enter the realm between the stars. This historic crossing was confirmed after careful analysis of subsequent data, marking a milestone in human exploration as significant as the first satellite in orbit, the first human in space, or the first footsteps on the Moon. Voyager 2 followed a somewhat different trajectory and crossed the heliopause on November 5, 2018, at a distance of 119 astronomical units from the Sun. By crossing into interstellar space at a different location than Voyager 1, the second spacecraft provided valuable comparative data that helped scientists better understand the structure and dynamics of the heliopause boundary. One of the most significant insights to emerge from these dual crossings is that the heliopause is not a static boundary, but a dynamic one that moves and changes in response to variations in both the solar wind and the interstellar medium. The Sun goes through an 11-year cycle of activity, with periods of high activity featuring numerous sunspots, solar flares, and coronal mass ejections that enhance the solar wind. During these active periods, the increased solar wind pressure pushes the boundaries of the heliosphere outward. Conversely, during solar minimum, when the Sun is less active, the boundaries contract inward. This breathing of the heliosphere means that the actual distance to the heliopause can vary by several astronomical units over time. It also creates complex wave structures that propagate through the heliosheath and can temporarily distort the shape of the boundary. The timing of the Voyager crossings, which occurred during different phases of the solar cycle, has allowed scientists to begin mapping these fluctuations. The two Voyager crossings also revealed something unexpected about the interstellar magnetic field just beyond the heliopause. Rather than being randomly oriented, this field appears to be draped around the heliosphere, compressed and aligned by the pressure of our solar bubble as it moves through the interstellar medium. This draping effect creates a region just outside the heliopause, where the interstellar magnetic field is stronger and more ordered than it is in the undisturbed interstellar medium farther away. The particles detected in this region have also provided insights into the composition of the local interstellar medium. While astronomers had been able to make remote observations of interstellar gas and dust for decades, the Voyagers offered the first opportunity to directly sample this material. These measurements confirmed that the local interstellar medium contains primarily hydrogen and helium, with traces of heavier elements, consistent with the overall composition of the galaxy. However, they also revealed variations in density and temperature that suggest our Sun may be traveling through a localized cloud of slightly warmer, less dense material within the broader interstellar medium. While the Voyagers have provided our most direct observations of the edge of the solar system, they are not the only spacecraft contributing to our understanding of this region. NASA's Interstellar Boundary Explorer, or IBEX, launched in 2008, uses a different approach. Rather than traveling to the boundary, IBEX remains in Earth orbit and detects energetic neutral atoms that are created in the outer heliosphere and travel inward toward the Sun. These atoms, which are not affected by magnetic fields because they carry no charge, provide a way to remotely sense the distant boundary regions. IBEX has made several significant discoveries, including the detection of a ribbon of enhanced energetic neutral atom emissions that stretches across the sky. This ribbon appears to be aligned with the direction of the interstellar magnetic field as it drapes around the heliosphere, providing additional evidence for the complex interaction between our solar bubble and the surrounding interstellar environment. The spacecraft has also observed changes in this ribbon over time, confirming the dynamic nature of the heliospheric boundary. Another mission, NASA's Advanced Composition Explorer, or ACE, has been monitoring the solar wind from a position near Earth since 1997. By providing continuous measurements of the solar wind properties as they exist near Earth, ACE helps scientists understand the conditions that, after a journey of more than a year, will reach the outer boundaries of the heliosphere. This information is crucial for interpreting the observations made by the Voyagers and other distant spacecraft. The combined data from these missions has allowed scientists to create increasingly sophisticated models of the heliosphere and its boundaries. These models, often run on supercomputers, simulate the complex plasma physics that governs the interaction between the solar wind and the interstellar medium. They have evolved from simple spherical approximations to detailed three-dimensional representations that account for the sun's motion through space, the influence of the interstellar magnetic field, and the variations caused by the solar cycle. One of the most interesting aspects of this research is what it reveals about the protective function of the heliosphere. Our sun's bubble shields the inner solar system from some of the galactic cosmic rays that permeate the galaxy. These high-energy particles, primarily protons and heavier nuclei, accelerated to nearly the speed of light by distant supernovae, black holes, and other cosmic accelerators, can damage living tissue and electronic components. The heliosphere's magnetic field deflects some of these particles, reducing the radiation exposure of the planets. Studies of the heliospheric boundary have shown that this shielding effect varies over time. During periods of high solar activity, when the heliosphere is expanded and its magnetic field is stronger, the shielding is more effective. During solar minimum, more cosmic rays can penetrate to the inner solar system. This variation has implications for space travel, particularly for lengthy missions to Mars or beyond, where astronauts would be exposed to increased radiation during solar minimum periods. The heliosphere also protects against interstellar dust to some extent. The solar wind, plasma, and magnetic field can deflect or slow the smallest dust particles, preventing them from reaching the inner solar system. Larger dust grains, with greater momentum, can penetrate deeper into the heliosphere, but are still affected by its boundary regions. This filtering effect influences the amount and composition of interstellar material that can reach Earth and the other planets, potentially affecting the chemistry of planetary atmospheres over long time scales. Beyond its protective function, the heliosphere serves as an exemplar for understanding similar structures around other stars. Observations have revealed that many stars have their own stellar winds and likely create their own astrospheres, the general term for the bubble of influence surrounding a star. By studying our own heliosphere in detail, scientists can make inferences about these distant stellar systems and how they interact with the interstellar medium in different regions of the galaxy. This comparative perspective becomes particularly interesting when considering stars that are traveling through denser regions of the interstellar medium or that have weaker stellar winds than our Sun. In such cases, the astrosphere might be much more compressed, potentially allowing more interstellar material and cosmic rays to reach any planets orbiting these stars. Conversely, younger or more active stars might create more extensive protective bubbles. These variations could have significant implications for the development and sustainability of life on any planets in these systems. Our understanding of the edge of the solar system continues to evolve as the Voyager spacecraft venture farther into interstellar space and newer missions provide additional data. One of the most intriguing developments is the growing recognition that the boundary between the solar system and interstellar space is not just a physical or magnetic boundary, but also a chemical one. The solar system formed from a specific cloud of gas and dust about 4.6 billion years ago, with a particular isotopic composition that differs slightly from the average composition of the galaxy. This solar system material has been processed through the Sun and redistributed throughout the planets, moons, and smaller bodies. The boundary where this processed solar material gives way to pristine interstellar matter represents yet another definition of the edge of the solar system, one that may not perfectly align with the heliopause or other physically defined boundaries. Studies of the isotopic compositions of interstellar particles detected by spacecraft have begun to map this chemical boundary, providing insights into the original formation of our solar system and how it differs from the surrounding galaxy. This research connects the exploration of the heliospheric boundary to broader questions about the origin and evolution of our cosmic neighborhood. Another emerging area of research involves the very definition of the solar system's edge. While the heliopause marks the boundary of the Sun's plasma influence, the gravitational influence of the Sun extends much farther. The hypothesized Oort cloud, a vast spherical shell of icy bodies thought to surround the solar system at distances of 1,000 to 100,000 astronomical units, remains gravitationally bound to the Sun despite lying far beyond the heliopause. In this sense, the outer edge of the Oort cloud, where the Sun's gravitational influence becomes weaker than that of neighboring stars and the galactic tide, might be considered the true edge of the solar system. However, no spacecraft has yet reached the Oort cloud, and none of our current vehicles will do so within their operational lifetimes. Voyager 1, the fastest and most distant spacecraft, would take about 300 years to reach the inner edge of the Oort cloud and 30,000 years to pass through it entirely. This remote region remains observational only through the rare comets that orbital perturbations occasionally send inward toward the Sun. The layered nature of the solar system's edge, with different boundaries defined by different physical phenomena, underscores the complexity of this transition region. Rather than a simple border between here and there, the edge of the solar system is a multifaceted frontier where different aspects of solar influence gradually give way to the broader galactic environment. This complexity is further illustrated by recent discoveries regarding the shape of the heliosphere. Traditional models depicted the heliosphere as a comet-like structure, with a roughly spherical head facing the direction of the Sun's travel through the galaxy and a long tail streaming behind. However, data from the Voyagers and IBEX have suggested a different shape, possibly more like a croissant or deflated balloon, without the extended tail previously envisioned. Some models even suggest a more spherical shape, with the solar wind deflected around the flanks of the heliosphere rather than streaming directly backward. These revisions to our understanding of the heliosphere's shape have implications for how effectively it shields different regions of the solar system from interstellar influences. A more compact, tailless heliosphere would mean that the outer planets experience more similar protective conditions regardless of the Sun's direction of travel through the galaxy. Conversely, an extended tail would create a directional aspect to this shielding, potentially relevant over very long timescales as the Sun orbits the galactic center. The study of the heliosphere's boundary has been enhanced by considering similar structures around other planets. Jupiter, Saturn, Uranus, and Neptune all generate their own magnetospheres, miniature versions of the heliosphere, where planetary magnetic fields carve out bubbles within the solar wind. These planetary magnetospheres display many of the same features as the heliosphere, including bow shocks where the solar wind first encounters the magnetic obstacle, magnetopauses, where the planetary magnetic field pressure balances the solar wind pressure, and magnetotails that stretch away from the Sun. By studying how these smaller boundaries respond to changes in the solar wind, scientists can better understand the dynamics of the much larger heliospheric boundary. The rapid response of planetary magnetospheres to solar events provides a laboratory for processes that occur much more slowly at the edge of the solar system, where a disturbance in the solar wind might take months or years to produce an observable effect. An additional perspective comes from studying the boundaries around comets. As these icy bodies approach the Sun, they develop atmospheres or comas of gas and dust that interact with the solar wind to form complex boundaries, including bow shocks and magnetotails of their own. These temporary structures, which form and dissipate over periods of weeks or months as comets move through the inner solar system, provide yet another window into the physics of boundaries in space plasma environments. One of the most fascinating aspects of the heliospheric boundary is its role as a selective filter for cosmic rays and interstellar particles. Different types of particles experience the boundary differently based on their charge, mass, and energy. Charged particles like protons and electrons are strongly affected by the magnetic fields in the boundary region, with low-energy particles largely excluded from entering the heliosphere. Neutral particles, in contrast, can cross the boundary relatively unimpeded, though they may become charged through interactions with other particles and subsequently become trapped in the heliospheric magnetic field. This filtering effect creates a unique particle environment within the heliosphere that differs from the broader galaxy. The specific mix of particles that reaches Earth and the other planets is determined by this selective boundary, influencing everything from space, weather, and atmospheric chemistry to radiation exposure for astronauts and even the long-term evolution of life. Research into the boundary's filtering properties therefore connects to fields as diverse as astrobiology, climate science, and human space exploration. The dynamic nature of the heliospheric boundary also means that this filtering effect varies over time. During periods of high solar activity, the expanded heliosphere and strengthened magnetic field provide enhanced shielding against galactic cosmic rays. During solar minimum, the contracted heliosphere allows more cosmic rays to penetrate to the inner solar system. This variation creates a natural experiment that has been ongoing throughout Earth's history, potentially influencing climate and even biological evolution through changing radiation environments. On even longer timescales, the Sun's journey through the galaxy takes it through regions of differing interstellar density. Currently, the Sun is traveling through what astronomers call the local interstellar cloud, a region of slightly higher density within the local bubble, a larger region of relatively low density created by ancient supernovae. In the distant past and future, the Sun has and will encounter denser interstellar clouds that would compress the heliosphere more severely, potentially allowing more interstellar material to penetrate to the inner solar system. Some researchers have suggested that these passages through denser interstellar regions could affect Earth's climate and environment. A compressed heliosphere would emit more galactic cosmic rays, which some studies suggest can influence cloud formation in Earth's atmosphere. Additionally, a greater influx of interstellar dust could alter the amount of sunlight reaching Earth's surface, potentially causing cooling episodes. These effects would occur on timescales of millions of years, as the Sun moves through different regions of the galaxy during its 230 million year orbit around the galactic center. The study of the heliospheric boundary thus connects to much broader questions about the solar system's place in the galaxy and how galactic environments influence planetary habitability over long time scales. This perspective has become increasingly relevant as astronomers discover more exoplanets orbiting other stars, each with its own relationship to its stellar wind and the surrounding interstellar medium. For stars in more crowded regions of the galaxy, such as globular clusters or the galactic center, the interstellar medium is denser and interactions with neighboring stars more frequent. Planets in these environments might experience more variable conditions as their host stars move through regions of differing density or encounter shock waves from nearby supernovae. Conversely, stars in less dense regions might maintain more stable protective bubbles, potentially providing more consistent conditions for any planets they host. The heliospheric boundary also serves as a natural laboratory for studying fundamental plasma physics processes that are relevant throughout the universe. Phenomena like magnetic reconnection, where magnetic field lines break and reconnect, releasing energy and accelerating particles, occur at the heliopause and in the heliosheath. Similar processes occur in solar flares, Earth's magnetosphere, and even in the accretion disks around black holes and neutron stars. By studying these processes at the edge of our solar system, where they can be measured directly by spacecraft, scientists gain insights that can be applied to more distant and extreme environments. Another intriguing aspect of the heliospheric boundary is its role in mediating the exchange of material between the solar system and the broader galaxy. While most people think of space as empty, it actually contains a diffuse gas of atoms and molecules, along with tiny dust particles. Some of this material originates within the solar system, ejected from the Sun through the solar wind, or released from comets and asteroids. Other material comes from interstellar space, either as part of the local interstellar cloud through which the Sun is currently traveling, or as more distant material carried by the galactic wind. The boundary regions of the heliosphere determine how these different sources of material mix and interact. Some solar material escapes into interstellar space, carrying with it isotopic signatures unique to our solar system. Similarly, some interstellar material penetrates into the heliosphere, bringing with it information about the composition and conditions of the nearby galaxy. By studying the exchange of material across the heliospheric boundary, scientists can better understand both the history of our solar system and the nature of our galactic neighborhood. This material exchange has practical implications for understanding the origin of certain isotopes found on Earth. For example, iron-60, a radioactive isotope with a half-life of about 2.6 million years, has been found in deep-sea deposits on Earth. Since this isotope decays relatively quickly on cosmic timescales, its presence suggests that it was deposited relatively recently, likely from the debris of a nearby supernova explosion that penetrated the heliosphere. Similar deposits of other isotopes may record other astronomical events that affected the heliospheric boundary in the past, providing a kind of cosmic archaeological record embedded in Earth's geology. The study of the heliospheric boundary also connects to one of the most fundamental questions in astrobiology, the potential for interstellar panspermia, the hypothesis that life might spread between star systems carried on dust particles or meteoroids. For such transfer to occur, biological material would need to survive not only the harsh conditions of interstellar space, but also the transition through the heliospheric boundary, with its complex electromagnetic fields and potential for inducing electrical charges on particles. Understanding the physics of this boundary helps assess the plausibility of such transfer mechanisms and constrains models of how life might spread through the galaxy. As our robotic emissaries continue their journeys into and through interstellar space, they provide an expanding dataset that continually refines our understanding of the solar system's edge. The Voyager spacecraft, though launched in the 1970s with technology that would be considered primitive by today's standards, continue to function and send back valuable data. Their power sources, radioisotope thermoelectric generators that convert the heat from decaying plutonium into electricity, will continue to provide sufficient energy for some instruments until around 2025, extending the mission's scientific returns nearly 50 years after launch. Even after the Voyagers fall silent, their legacy will continue through the New Horizons spacecraft, which, after its explorations of Pluto and the Kuiper Belt, is also headed toward the outer heliosphere. Though it will not overtake the Voyagers, New Horizons carries more modern instruments that will provide complementary data as it eventually approaches and crosses the same boundaries, likely in the 2030-40s. Future missions specifically designed to explore the heliospheric boundary in more detail have been proposed. Concepts like the Interstellar Probe would use advanced propulsion technologies to reach the heliopause much faster than previous spacecraft, perhaps within 10 to 15 years, rather than the 35+ years required by the Voyagers. Such a mission could carry a comprehensive suite of modern instruments, specifically designed to study the boundary regions and the interstellar medium beyond, potentially resolving many of the questions raised by our current explorers. Other proposed missions would take different approaches to studying this region. Some would focus on remote sensing, using energetic neutral atoms or other particles that can travel from the boundary regions to detectors near Earth. Others might deploy multiple smaller spacecraft to sample different regions of the heliosphere simultaneously, providing a more comprehensive picture of its structure and dynamics. Still others would focus on the interstellar medium itself, characterizing the environment into which our solar system is traveling and potentially identifying any features or disturbances that might affect the heliosphere in the coming decades or centuries. These future explorations will build on the foundation established by the Voyagers, IBEX, and other current missions, continuing humanity's systematic exploration of our solar system's furthest frontier. Just as the early maritime explorers who first ventured beyond sight of land discovered that the oceans were not uniform but contained complex currents, weather patterns, and biological provinces, our first ventures beyond the solar system are revealing a complex and dynamic interstellar environment with its own structures and processes. In a sense, the exploration of the heliospheric boundary represents the beginning of human contact with the truly cosmic environment beyond our solar neighborhood. While the distances to even the nearest stars remain far beyond our current technological reach, the interstellar medium that fills the space between stars is now directly accessible to our instruments. This medium, though incredibly tenuous by earthly standards, connects all stars in the galaxy in a vast network of gas, dust, magnetic fields, and radiation. By studying the point where our sun's influence gives way to this broader galactic environment, we take our first steps into a much larger cosmic context. The edge of the solar system thus represents not just a physical boundary, but a conceptual one, the frontier where our understanding of familiar solar processes transitions to the less familiar realm of interstellar and galactic phenomena. Like all frontiers, it is a region of discovery and surprise, where observations frequently challenge our preconceptions and force us to revise our models and theories. It is also a region of perspective, offering a vantage point from which to view our solar system as a whole, a tiny bubble of relative stability in the vast, dynamic ocean of the galaxy. As we continue to explore and understand this boundary, we gain not only scientific knowledge, but also a deeper appreciation of our place in the cosmos. The heliosphere, this vast bubble created and maintained by our Sun, has provided a relatively protected environment within which the Earth and the other planets have evolved over billions of years. The subtle interplay between solar influences and galactic ones, mediated by the complex boundary regions, has helped shape the conditions for life on our planet and potentially on others within our solar system. In the silent, invisible boundaries at the edge of the solar system, where the influence of our star gradually gives way to the broader influences of the galaxy, we find a profound metaphor for human exploration itself, always striving to push beyond the known, to understand the unfamiliar, and to place our existence in an ever larger context. The journey of our spacecraft through and beyond these boundaries mirrors our intellectual journey as a species, venturing ever outward in search of understanding, perspective, and connection to the universe that surrounds us. Beyond the protective bubble of our Sun's influence lies a vast cosmic ocean, the interstellar medium, a realm that our most distant spacecraft are now beginning to explore. This is not the perfect vacuum that many imagine space to be, but rather a tenuous, complex environment filled with gas, dust, magnetic fields, and energetic particles that fills the enormous gulfs between the stars. It is through this medium that our entire solar system moves as the Sun orbits the center of the galaxy, and it is this medium that our Voyager spacecraft now directly sample as they journey into the broader cosmos. The interstellar medium is the stuff between the stars, the material from which new stars and planets form, and the repository for matter expelled from aging stars. It is at once incredibly sparse and unimaginably vast. In the region near our solar system, the interstellar medium contains only about 0.1 atoms per cubic centimeter, a vacuum more perfect than anything we can create in laboratories on Earth. Yet this material extends across the entire Milky Way galaxy, filling a volume so enormous that despite its low density, it accounts for about 15% of the visible matter in our galaxy. The composition of the interstellar medium broadly reflects the overall composition of the universe, with hydrogen making up about 90%, helium about 9%, and all other elements comprising the remaining 1%. This material exists in several different states. Some regions contain neutral atomic gas, with individual atoms drifting through space. Others contain molecular gas, where atoms have combined to form molecules, primarily molecular hydrogen, but also more complex compounds like water, ammonia, methanol, and even complex organic molecules. Still, other regions contain ionized gas, or plasma, where the atoms have been stripped of one or more electrons by radiation from nearby stars or by cosmic ray impacts. Interspersed with this gas are tiny solid particles known as interstellar dust. These particles, ranging in size from molecules to grains a few micrometers across, are composed primarily of silicates, carbon compounds, and ice. Though they make up only about 1% of the mass of the interstellar medium, these dust grains play a crucial role in the chemistry and physics of interstellar space. They provide surfaces on which molecular reactions can occur. They shield the interior of dense clouds from damaging radiation, and they contribute to the heating and cooling of interstellar gas through interactions with starlight and cosmic rays. The interstellar medium is not uniformly distributed, but exists in several distinct phases with different densities and temperatures. The hot ionized medium consists of gas heated to millions of degrees, primarily by shock waves from supernova explosions. This phase has an extremely low density, but fills much of the volume of the galaxy. The warm ionized medium and warm neutral medium have temperatures of about 8,000 and 6,000 degrees Kelvin respectively, with somewhat higher densities. The cold neutral medium, with temperatures of about 100 degrees Kelvin, forms diffuse clouds that can eventually condense into the densest phase, the molecular clouds, where temperatures drop to about 10 degrees Kelvin and densities rise to hundreds or thousands of molecules per cubic centimeter. It is within these cold, dense molecular clouds that new stars and planetary systems form. Permeating the interstellar medium are magnetic fields that, while incredibly weak by terrestrial standards, shape the dynamics of the gas and dust over vast distances. These fields guide the movement of charged particles, influence the collapse of gas clouds during star formation, and help distribute energy from stellar and supernova explosions throughout the galaxy. The galactic magnetic field has a strength of only about 1/10,000th of Earth's magnetic field, but it extends across thousands of light years. Also threading through the interstellar medium are cosmic rays, high-energy particles that travel through space at nearly the speed of light. These particles, primarily protons but also including heavier nuclei and electrons, have been accelerated to enormous energies by various cosmic accelerators, including supernova explosions, black holes, and other extreme environments. They permeate the galaxy, carrying with them energy and information about distant, violent processes. When cosmic rays interact with interstellar gas and dust, they can ionize atoms, trigger chemical reactions, and produce secondary particles and radiation, further influencing the complex chemistry of interstellar space. Until recently, our understanding of the interstellar medium came entirely from remote observations. Astronomers studied the absorption of starlight by interstellar gas and dust, measured radio emissions from atomic and molecular gas, and analyzed the deflection of cosmic rays by interstellar magnetic fields. These observations provided a broad picture of the interstellar environment, but many details remained uncertain, particularly regarding the specific conditions in the region of space through which our solar system is currently traveling. This changed with the historic journeys of the Voyager spacecraft. After completing their primary missions to the outer planets in the 1980s, these remarkable machines continued outward, eventually reaching the boundary between the solar system and interstellar space. Voyager 1 crossed this boundary, the heliopause, in August 2012, followed by Voyager 2 in November 2018. For the first time, human-made instruments were directly sampling the interstellar medium, providing in situ measurements that could confirm or challenge our understanding based on remote observations. The Voyager's instruments revealed several important features of the nearby interstellar medium. They confirmed that this region is dominated by neutral hydrogen gas, with a temperature of about 7,500 degrees Kelvin, consistent with the warm, neutral medium phase. They measured the strength of the interstellar magnetic field at around 0.48 nanoteslas, somewhat stronger than had been predicted by some models. And they detected a higher than expected density of low-energy cosmic rays, particles that had been excluded from the inner solar system by the Sun's magnetic field, but are apparently abundant in nearby interstellar space. One of the most significant discoveries was the orientation of the interstellar magnetic field. The Voyagers found that this field is inclined at a substantial angle to the plane of the galaxy, different from the general alignment of the galactic magnetic field. This suggests that our solar system is currently traveling through a localized disturbance or structure within the broader interstellar medium, possibly related to ancient supernova explosions that created a region known as the local bubble, within which our Sun and nearby stars reside. The Voyagers also detected waves and turbulence in the interstellar plasma, indicating that the interaction between our heliosphere, the bubble of solar influence, and the surrounding interstellar medium is dynamic and complex. As the Sun moves through the galaxy at a speed of about 20 kilometers per second, it creates a disturbance in the interstellar medium similar to the bow wave in front of a moving ship. The precise nature of this disturbance, whether it constitutes a true shock wave or a more gentle bow wave, depends on the speed of the Sun relative to the local speed of sound in the interstellar medium. Current evidence suggests that our Sun is moving just below the critical speed necessary to form a shock, creating a bow wave rather than a bow shock ahead of the heliosphere. This interaction between the heliosphere and the interstellar medium has important implications for the conditions within our solar system. The shape and size of the heliosphere determined by the balance between outward solar wind pressure and inward interstellar pressure, affects how well the inner solar system is shielded from galactic cosmic rays. These high-energy particles can damage living tissue and electronic components, making them a significant concern for space travel beyond Earth's protective magnetic field. They may also influence weather and climate on Earth through their potential effects on cloud formation. The heliosphere's effectiveness as a shield varies with the solar cycle and with changes in the surrounding interstellar environment as the Sun moves through different regions of the galaxy. Beyond the direct measurements from the Voyager spacecraft, our understanding of the interstellar medium has been enhanced by other space-based observatories. NASA's Interstellar Boundary Explorer, or IBEX, launched in 2008, detects energetic neutral atoms that are created at the boundary between the solar system and interstellar space and travel inward toward Earth. These atoms provide information about the interaction between the solar wind and the interstellar medium, allowing scientists to map the shape of the heliosphere and study the properties of the nearby interstellar environment without actually sending spacecraft to these distant regions. One of IBEX's most surprising discoveries was the detection of a ribbon of enhanced energetic neutral atom emissions that stretches across the sky. This ribbon appears to trace the direction where the interstellar magnetic field drapes around the heliosphere, providing further evidence for the complex interaction between our solar bubble and the surrounding galactic environment. The intensity and structure of this ribbon have been observed to change over time, reflecting the dynamic nature of the heliospheric boundary and possibly the passage of disturbances through the local interstellar medium. Another important mission is the Cosmic Ray Isotope Spectrometer aboard NASA's Advanced Composition Explorer, which has been measuring the isotopic composition of cosmic rays since 1997. By determining the precise mix of different isotopes in cosmic ray particles, scientists can infer information about their sources and about the material through which they have traveled. Some cosmic rays originate in nearby supernova explosions, while others come from more distant sources or from outside our galaxy entirely. The isotopic signatures help distinguish these different populations and provide insights into the various mechanisms that accelerate particles to such extreme energies. A particularly significant cosmic ray component is the anomalous cosmic rays, which originate from neutral atoms in the nearby interstellar medium that enter the heliosphere, become ionized by solar radiation, and are then accelerated to moderate energies at the termination shock or in the heliosheath. These particles provide a direct sample of the elemental composition of the local interstellar gas, complementing the in situ measurements made by the Voyagers as they cross into interstellar space. The ongoing exploration of the interstellar medium by these various missions has revealed it to be far more complex and dynamic than previously thought. Rather than a uniform, unchanging environment, the region through which our solar system is traveling shows evidence of structures, disturbances, and variations that reflect its history and connection to broader galactic processes. This complexity has implications not only for our understanding of the present conditions in nearby space, but also for reconstructing the history of our solar system's journey through the galaxy, and for predicting the environments it will encounter in the future. One fascinating aspect of this research is the evidence that our solar system has passed through different interstellar environments over its 4.6 billion year history. The Sun's orbit around the galactic center takes about 230 million years to complete, and during this journey, it passes through regions of differing density, temperature, and radiation environment. Currently, the Sun appears to be located within a relatively low-density region called the local interstellar cloud, itself part of a larger low-density region called the local bubble. This bubble, stretching hundreds of light-years across, was likely created by multiple supernova explosions within the last 10 to 20 million years. Prior to entering the local bubble, the Sun would have traveled through denser regions of the interstellar medium, where the heliosphere would have been more compressed by the higher external pressure. Some researchers have proposed that these passages through denser interstellar clouds could have affected Earth's climate by allowing more cosmic rays to penetrate to the inner solar system, potentially influencing cloud formation in Earth's atmosphere. There's also evidence from deep-sea deposits that Earth has occasionally been sprinkled with cosmic dust from the dense interstellar clouds through which the solar system has passed, some of which contains isotopes like iron-60 that indicate nearby supernova explosions. Looking to the future, Astronomical observations and computer models suggest that the solar system is gradually approaching the edge of the local bubble and may, within the next few million years, enter a region of somewhat higher density. This transition would likely cause the heliosphere to contract, potentially increasing the cosmic ray flux at Earth and the other planets. While such changes occur on timescales far longer than human history, they are relevant for understanding the long-term environment and evolution of our planetary system. The study of cosmic rays themselves presents a fascinating window into some of the most energetic processes in the universe. These particles span an extraordinary range of energies, from relatively modest accelerations comparable to those achieved in Earth-based particle accelerators to ultra-high energy cosmic rays that carry millions of times more energy than any particle produced in human laboratories. The most energetic cosmic rays detected possess energies equivalent to a baseball, traveling at about 100 kilometers per hour, but concentrated in a single subatomic particle, an almost unimaginable concentration of energy. Where do these extraordinary particles come from? The lower and middle energy cosmic rays are generally attributed to supernova explosions within our galaxy. When a massive star reaches the end of its life and explodes, the expanding shock wave can accelerate particles to high energies through a process called diffusive shock acceleration. Essentially, particles bounce back and forth across the shock front, gaining energy with each crossing until they eventually escape into the galaxy as cosmic rays. This process is remarkably efficient, converting up to 10% of the kinetic energy of the supernova explosion into cosmic ray acceleration. For the highest energy cosmic rays, however, even supernovae may not be powerful enough accelerators. These extraordinary particles, which fortunately strike Earth very rarely, are thought to originate from even more extreme environments, such as the jets of active galactic nuclei, powered by supermassive black holes, or from the mysterious gamma-ray bursts, the most luminous explosions known in the universe. Some may even have extragalactic origins, traveling across millions or billions of light years before reaching our solar system. Once accelerated, cosmic rays travel through the interstellar and intergalactic medium, deflected and scattered by magnetic fields that permeate space. Because of these deflections, even the highest energy cosmic rays do not travel in straight lines, making it difficult to trace them back to their exact sources. Instead, they arrive at Earth from seemingly random directions, creating an approximately isotropic flux across the sky. Only at the very highest energies, where the magnetic deflection is less significant, do some cosmic rays retain enough directional information to be potentially associated with specific astronomical objects. During their travels, cosmic rays interact with the interstellar medium in various ways. They can ionize neutral atoms, creating free electrons that then influence the chemistry and physics of interstellar clouds. They can penetrate dust grains, causing radiation damage that alters their structure and composition. And they can collide with other atoms, producing cascades of secondary particles and radiation that further influence the interstellar environment. These interactions make cosmic rays an important source of energy in the otherwise cold, dark reaches of interstellar space, driving chemical reactions that would not occur in their absence and helping to maintain the observed temperature of various phases of the interstellar medium. When cosmic rays encounter the heliosphere, they face an obstacle to their continued travel. The solar wind, carrying the sun's magnetic field, shapes and deflects these incoming particles. Lower energy cosmic rays, particularly those below about 1 billion electron volts, are significantly deflected or even prevented from entering the inner solar system. Higher energy particles penetrate more easily, but still experience some deflection and energy loss as they navigate the complex magnetic field environment of the heliosphere. This filtering effect varies with the solar cycle, with more cosmic rays reaching Earth during solar minimum, when the heliosphere is somewhat contracted and the solar magnetic field is less turbulent. Those cosmic rays that do reach Earth's vicinity then encounter another obstacle, our planet's magnetic field. This field deflects many of the remaining lower energy particles, especially near the equator where the magnetic field lines run parallel to the surface. Near the poles, where the magnetic field lines plunge into the planet, more cosmic rays can penetrate to the atmosphere. This is why aurora displays, which are partly enhanced by cosmic ray interactions, are more common near the polar regions. Finally, cosmic rays that reach Earth's atmosphere collide with air molecules, creating cascades of secondary particles called air showers. A single high-energy cosmic ray can generate billions of secondary particles that spread out as they travel toward the ground. These include charged particles like electrons, muons, and protons, as well as neutral particles like neutrons and photons. Some of these reach the ground, where they can be detected by specialized observatories. Others decay or are absorbed in the atmosphere, transferring their energy to the air molecules and contributing to the ionization of the upper atmosphere. The constant shower of cosmic rays at Earth's surface exposes all living things to a low but persistent level of radiation. The typical dose at sea level is about 0.1 millisieverts per year, a small fraction of the total background radiation we receive from all sources. However, at high altitudes, such as those experienced during air travel, the cosmic ray exposure increases significantly because there is less protective atmosphere above. Airline crew members who frequently fly at high altitudes and over polar routes can receive annual cosmic ray doses that approach occupational radiation limits. In space, beyond Earth's protective magnetic field and atmosphere, cosmic ray exposure becomes a major concern for astronaut health, particularly for long-duration missions to the Moon or Mars. Despite these hazards, cosmic rays also serve as valuable scientific tools. By studying the cosmic rays that reach Earth, scientists can infer information about their sources, about the interstellar medium through which they have traveled, and about fundamental particle physics at energies beyond those achievable in terrestrial accelerators. Cosmic ray detectors range from small instruments carried on balloons or spacecraft to enormous ground-based arrays covering many square kilometers, designed to catch the rare, ultra-high energy events. One of the most remarkable cosmic ray observatories is the Pierre Auger Observatory in Argentina, which combines 4,000 surface detectors spread over 3,000 square kilometers, with 27 fluorescence telescopes that watch for the faint flashes of light produced when cosmic ray air showers excite nitrogen molecules in the atmosphere. This hybrid approach allows scientists to measure both the distribution of particles at ground level and the development of the shower as it propagates through the atmosphere, providing complementary information about the energy and composition of the primary cosmic ray. Another innovative approach is represented by the IceCube Neutrino Observatory at the South Pole, which detects neutrinos, nearly massless particles that are produced in cosmic ray, air showers, and in various astrophysical sources like supernovae and active galactic nuclei. Neutrinos interact extremely weakly with matter, making them difficult to detect but also allowing them to travel cosmological distances without being deflected by magnetic fields or absorbed by intervening matter. The IceCube detector consists of thousands of optical sensors buried deep in the Antarctic ice, watching for the rare occasions when a neutrino interacts with a water molecule and produces a flash of light. By detecting neutrinos associated with cosmic ray sources, scientists can obtain information complementary to that provided by direct cosmic ray measurements. These and other observatories form a global network studying cosmic rays across a vast range of energies, from less than 1 million electron volts to more than 1 billion electron volts, a span of over 15 orders of magnitude. This research connects the study of the interstellar medium to fundamental questions in particle physics, astrophysics, and cosmology. What are the limits of particle acceleration in the universe? How do the most energetic objects, like black holes and gamma-ray bursts, function? How do magnetic fields permeate and influence the space between galaxies? What role did cosmic rays play in the evolution of galaxies and in establishing the conditions for the formation of stars and planets? These questions illustrate how the study of the seemingly empty space between the stars and the energetic particles that permeate it connects to some of the most profound questions in our understanding of the universe. The interstellar medium is not merely the absence of stars, but a complex, dynamic system with its own physics, chemistry, and evolution, intimately connected to the life cycles of stars and galaxies. For our solar system, the interstellar medium represents both the environment through which we are currently traveling and the source material from which our planetary system originally formed. The gas and dust of the interstellar medium, enriched by the remnants of previous generations of stars, condensed to form the Sun and its family of planets about 4.6 billion years ago. The specific composition of this material including the abundance of elements heavier than hydrogen and helium, determined the nature of the planets that could form and, ultimately, the possibility of life on at least one of those planets. The connection between the interstellar medium and the origin of life extends beyond the mere provision of raw materials. Cosmic rays may have played a role in the prebiotic chemistry that eventually led to the emergence of life on Earth. When cosmic rays interact with molecules in planetary atmospheres or on planetary surfaces, they can induce chemical reactions that create complex organic compounds, including some of the building blocks of life, like amino acids and nucleobases. Evidence for this process comes from laboratory experiments that simulate cosmic ray interactions with simple atmospheric gases, and from the detection of complex organic molecules in meteorites that have been exposed to cosmic radiation in space. Some researchers have proposed that cosmic rays might also influence the evolution of life through their mutagenic effects on DNA. The radiation dose from cosmic rays is generally low enough that it does not pose an acute danger to life on Earth's surface, but over geological timescales, cosmic ray-induced mutations might have contributed to the genetic diversity that drives evolution. This effect would be more pronounced during periods when Earth's magnetic field was weaker, or when the solar system passed through denser regions of the interstellar medium, allowing more cosmic rays to reach the planetary surface. The relationship between cosmic rays and Earth's climate represents another potential link between the interstellar medium and conditions on our planet. Some climate scientists have proposed that cosmic rays might influence cloud formation by ionizing air molecules, which then serve as nucleation sites for water droplets. According to this hypothesis, variations in the cosmic ray flux due to changes in solar activity or in the interstellar environment might influence Earth's cloud cover and, consequently, its energy balance and climate. While this hypothesis remains controversial, with many climate scientists arguing that the effect is too small to significantly impact climate compared to other factors like greenhouse gases, it illustrates how processes originating in the interstellar medium might have unexpected connections to phenomena much closer to home. For future human exploration beyond Earth, the interstellar medium and cosmic rays represent significant challenges. Any lengthy journey beyond the protection of Earth's magnetic field, such as a mission to Mars or beyond, would expose astronauts to increased radiation from galactic cosmic rays. Unlike solar radiation, which can be predicted and sheltered from during solar storms, cosmic ray radiation is constant and difficult to shield against because of the high energy of the particles involved. Thick layers of shielding material can block some cosmic rays, but they can also create secondary particles when high-energy cosmic rays fragment upon hitting the shield, potentially increasing the radiation dose inside the spacecraft. Developing effective protection strategies for astronauts on long-duration deep space missions remains an active area of research in space medicine and engineering. Despite these challenges, the human dream of someday venturing beyond our solar system to explore the stars implies an eventual direct encounter with the interstellar medium. While such journeys remain firmly in the realm of science fiction with current technology, they are not impossible in principle. Various concepts for interstellar probes have been proposed, from nuclear pulse propulsion to laser-pushed light sails, but all would need to address the challenges posed by the interstellar environment, including impacts with interstellar dust, interaction with interstellar magnetic fields, and shielding from cosmic radiation. One of the most ambitious current initiatives in this direction is Breakthrough Starshot, a project announced in 2016 with the goal of sending a fleet of tiny spacecraft, each weighing just a few grams, to the nearest star system, Alpha Centauri, which lies about 4.3 light-years from Earth. The proposed spacecraft would be accelerated to about 20% of the speed of light using powerful ground-based lasers, allowing them to reach Alpha Centauri in about 20 years. At such speeds, even impacts with tiny interstellar dust grains could be catastrophic, and the spacecraft would need to be designed to withstand or avoid such collisions, as well as to navigate through the interstellar magnetic field and tolerate the cosmic ray environment. While actual interstellar travel remains a distant prospect, our robotic explorers continue to push the boundaries of our reach. The Voyager spacecraft, having crossed the heliopause, are now truly interstellar travelers, sampling directly the environment between the stars. Though their power sources will fail within the next decade, they will continue their silent journeys through the interstellar medium indefinitely, reaching a distance of about 2 light-years from the Sun in the next 40,000 years. They may someday be the first human-made objects to encounter another star system, though the odds of such an encounter are very low given the vast emptiness of interstellar space. In the meantime, our understanding of the interstellar medium continues to advance through both direct sampling by spacecraft and remote observations by ground and space-based telescopes. New observatories like the James Webb Space Telescope provide unprecedented views of the interstellar medium in both our galaxy and distant ones, revealing the processes of star formation, the cycling of matter between stars and the interstellar environment, and the role of cosmic dust in shaping the evolution of galaxies. Radio telescopes like the Atacama Large Millimeter Array map the distribution and motion of molecular gas in interstellar clouds, showing the intricate structures that eventually collapse to form new stars and planetary systems. These observations are complemented by increasingly sophisticated computer simulations that model the complex physics of the interstellar medium across a wide range of scales, from the turbulent dynamics of individual molecular clouds to the global circulation patterns that distribute gas throughout the galaxy. These simulations help interpret observational data and test theories about the processes that shape the interstellar environment, including the role of gravity, magnetic fields, radiation, and cosmic rays. One of the most fascinating aspects of interstellar medium research is how it connects microscopic and macroscopic processes across vast ranges of scale. The same magnetic fields that deflect individual cosmic ray particles over distances of light years also help regulate the formation of stars and the evolution of entire galaxies. The dust grains that form in the outflows of dying stars become the building blocks for new planetary systems. The heavy elements synthesized in supernova explosions are dispersed through the interstellar medium, eventually becoming incorporated into new generations of stars and planets, including the elements that make up Earth and all living things upon it. This interconnection is reflected in the concept of the galactic ecosystem, in which matter cycles between stars and the interstellar medium in a grand, cosmic version of the elemental cycles familiar from Earth's biosphere. Stars form from the gravitational collapse of interstellar clouds, fuse hydrogen and other light elements into heavier ones in their cores, and eventually return much of their material to the interstellar medium through stellar winds or supernova explosions, enriched with the products of nuclear fusion. This enriched material then becomes part of new interstellar clouds, which collapse to form new stars, continuing the cycle. Over the 13.8 billion year history of our universe, this process has gradually increased the abundance of elements heavier than hydrogen and helium, making possible the formation of rocky planets and, ultimately, life itself. The interstellar medium thus serves as both cradle and grave for stars and planetary systems, the source from which they form, and the repository to which much of their material eventually returns. Our own solar system represents just one brief phase in this grand cycle, a temporary concentration of material gathered from the interstellar medium, shaped by gravity, radiation, and time into the Sun and its family of planets, moons, asteroids, and comets. Eventually, in about 5 billion years, when the Sun exhausts its nuclear fuel and expands to become a red giant before shedding its outer layers as a planetary nebula, much of this material will return to the interstellar medium, potentially to be incorporated into future stellar and planetary systems. In contemplating these vast cycles of matter and energy that connect our solar system to the broader galaxy, we gain a deeper perspective on our place in the cosmos. The atoms that make up Earth and all living things upon it have existed since shortly after the Big Bang, but they have been part of other stars, other planets, and the interstellar medium itself over the course of cosmic history. The carbon in our bodies was forged in the hearts of massive stars that exploded as supernovae billions of years ago. The oxygen we breathe was created in similar stellar furnaces. The iron in our blood carries the signature of ancient cosmic cataclysms. This perspective reveals a profound connection between human existence and the seemingly remote and abstract realm of the interstellar medium. We are not merely observers of the cosmos, but products of it, assembled from materials that have participated in the grand cycles of galactic evolution. The interstellar medium, far from being empty space, is a vital component of this cosmic ecosystem, the medium through which matter and energy flow between generations of stars and planetary systems. As our robotic explorers venture beyond the heliopause and into true interstellar space, they carry with them this recognition of our cosmic heritage. They sample directly the environment from which we ultimately came and to which the material of our solar system will someday return. In their silent journeys through the void between the stars, they embody humanity's curiosity about our origins and our place in the universe, extending our presence, if only through these tiny mechanical ambassadors, into the vast ocean of the interstellar medium. The story of the interstellar medium and cosmic rays is thus not a tale of empty space and invisible radiation, but a chapter in the broader narrative of cosmic evolution, a narrative that includes the formation of galaxies, the birth and death of stars, the origin of planets, and the emergence of life. It is a story that connects the most distant regions of space and the most energetic processes in the universe to the very atoms of our bodies and the air we breathe. In exploring the nature of the interstellar medium and the particles that permeate it, we are, in a very real sense, exploring our own cosmic origins and the processes that made our existence possible. The Voyager spacecraft, as they journey through this environment, serve as our proxies, experiencing directly what we can otherwise only study remotely or simulate in computers. Their measurements of the interstellar magnetic field, the density and composition of the interstellar gas, and the properties of cosmic rays beyond the heliopause provide ground truth for our models and theories, connecting abstract astrophysical concepts to specific, quantifiable realities. Though their active scientific mission will soon end as their power sources fade, they have already transformed our understanding of the environment that lies beyond our solar system, revealing it to be complex, dynamic, and intimately connected to the broader processes of galactic evolution. As we look to the future, new missions will extend this exploration, building on the foundation laid by the Voyagers and other spacecraft. Proposed interstellar probe missions would venture deliberately into the nearby interstellar medium, carrying modern instruments specifically designed to study this environment in detail. Future space-based observatories will map the structure and composition of the interstellar medium throughout our galaxy and beyond with unprecedented resolution and sensitivity. And advanced computer simulations will continue to refine our understanding of the complex physics that governs the behavior of this seemingly empty but actually rich and dynamic realm. Through these efforts, we will continue to deepen our understanding of the interstellar medium and cosmic rays, not merely as abstract scientific concepts, but as vital components of the cosmic environment that shaped our solar system and made possible the emergence of life on Earth. In studying the space between the stars and the energetic particles that fill it, we are studying our own cosmic context and heritage, expanding our awareness beyond the confines of our planetary home to encompass the vast, interconnected system of which we are a part. As we drift towards sleep, let us contemplate this profound connection between our seemingly mundane existence and the exotic realm of the interstellar medium. Let us imagine the Voyager spacecraft, tiny specks of human ingenuity, now adrift in the vast ocean between the stars, sampling directly the environment from which the materials of our world and our bodies ultimately came. And let us recognize that in exploring the most distant and abstract domains of the cosmos, we are, in a very real sense, coming to know ourselves and our place in the grand tapestry of cosmic evolution that connects all things, from the smallest particles to the largest structures, in an intricate, interconnected whole. As our robotic explorers journey into the cosmic ocean beyond our solar system, they carry with them more than scientific instruments and power systems. They bear messages from Earth, intentionally crafted communications that may someday, in the distant future, be the only evidence that humanity ever existed. These messages, physical artifacts of our civilization, represent one of the most profound and poignant aspects of our deep space missions, the possibility that they might someday be found by other intelligences, bringing news of Earth and its inhabitants to beings we can barely imagine across gulfs of time and space that stagger the mind. The story of these interstellar messages begins with the Pioneer missions of the early 1970s. As Pioneer 10 and 11 were being prepared for their journeys to Jupiter, Saturn, and eventually beyond the solar system, a small group of scientists, led by Carl Sagan, recognized a unique opportunity. These spacecraft would be the first human artifacts to leave the solar system, potentially traveling through interstellar space for millions or even billions of years. Though the chances of another civilization ever encountering them were infinitesimally small, the mere possibility warranted consideration. What if, against all odds, these emissaries of Earth were someday found by beings from another world? What would we want them to know about us? This question led to the creation of the Pioneer plaques, simple gold anodized aluminum plates attached to the antenna support struts of both Pioneer 10 and 11, measuring just 15 by 23 centimeters. These plaques were designed to convey basic information about humanity and our place in the universe through engravings that could potentially be deciphered by any technologically advanced civilization that might find them. The design of the Pioneer plaques, created by Carl Sagan, Frank Drake, and artist Linda Salzman Sagan, included several key elements. Most prominently, they featured the outlined figures of a human male and female, drawn to scale beside a silhouette of the spacecraft. The man's hand is raised in a gesture of greeting, a simple representation of human form and communication that might be recognized by beings who had never seen a human before. Near the bottom of the plaque is a diagram of our solar system, showing the 9 planets, as they were then categorized, and their distances from the Sun, with the trajectory of Pioneer indicated by an arrow from Earth. This diagram establishes where the spacecraft came from within our solar system and provides a basic representation of our astronomical neighborhood. Perhaps the most ingenious element of the plaque is the pulsar map in the upper left. This diagram shows the position of the Sun relative to 14 pulsars, rapidly rotating neutron stars that emit precisely timed radio pulses. Each pulsar is indicated with a line showing its distance and direction from the Sun, and its pulse frequency is noted in binary code. Since pulsars slow down at predictable rates, this information would allow a sufficiently advanced civilization to determine when the spacecraft was launched, even if it were found millions of years in the future. Essentially, it's a celestial coordinate system, a cosmic address that could lead finders of the plaque back to our solar system, regardless of how far the spacecraft had traveled. The upper right of the plaque contains a representation of the hyperfine transition of hydrogen, the most abundant element in the universe. When a hydrogen atom's electron flips its spin state, it emits energy at a specific wavelength, creating a natural unit of length and time. This provides a universal scale for the other diagrams on the plaque, allowing the finders to determine the actual size and timing information represented in the drawings. The creation of the Pioneer plaques marked the first time humans had deliberately sent a message to the stars, intended not for our contemporaries but for unknown beings in the distant future. It represented a new kind of communication, one that transcended not just the boundaries of language and culture, but of species and time itself. As Carl Sagan later wrote, the spacecraft will be encountered and the record played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. The Pioneer plaques, for all their ingenuity, were necessarily limited by their small size and the short time available for their design and production. When the opportunity arose a few years later to include a more comprehensive message aboard the Voyager spacecraft, Sagan and his colleagues embraced the chance to create something more elaborate. The result was the Voyager Golden Records, phonograph records made of gold-plated copper, 12 inches in diameter, which were attached to both Voyager 1 and Voyager 2 before their launches in 1977. These golden records represented a quantum leap in complexity compared to the Pioneer plaques. Instead of simple engravings, they contained actual sounds and images from Earth, encoded in analog form that could potentially be played back by whoever might find them. Each record contains 115 images, encoded as analog waveforms that could be converted back into pictures using the included equipment and instructions. These images range from scientific diagrams and anatomical drawings to photographs of human activities, natural landscapes, architecture, and wildlife from around the world, providing a visual encyclopedia of life on Earth. The records also contain audio recordings, including greetings in 55 human languages, from ancient Akkadian to modern Wu Chinese, along with printed greetings from the Secretary General of the United Nations and the President of the United States. There's a collection of sounds from Earth, including thunder, volcanoes, ocean waves, animal calls, and human-made sounds like footsteps, heartbeats, laughter, and the launch of a Saturn V rocket. Most extensively, the records contain 90 minutes of music from around the world, carefully selected to represent the diversity of human musical traditions. This collection ranges from Bach, Beethoven, and Mozart to Senegalese percussion, Japanese shakuhachi flute, Navajo chants, and Chuck Berry's Johnny B. Good. The selection process for this music involved lengthy debates among the committee members about which pieces best represented humanity's artistic achievements in a form that might be meaningful to beings with entirely different sensory and cognitive systems. The covers of the records include visual instructions for how to play them, based on the universal physical properties of the hydrogen atom. They also reproduce the pulsar map from the Pioneer plaques, providing the same cosmic return address for any finders. The records themselves are protected by aluminum cases, along with a needle and cartridge for playing them. The cases are sealed in a vacuum and include a small sample of uranium-238, whose half-life of 4.5 billion years provides a built-in radioactive clock. By measuring the remaining uranium, future finders could determine when the spacecraft was launched, even if they had no way to decode the pulsar map. The creation of the Golden Records was a monumental undertaking, involving dozens of scientists, artists, and engineers working under significant time constraints. The final product represented not just a technical achievement, but a profound cultural and philosophical statement about humanity's place in the cosmos and our desire to communicate across the vast gulfs of space and time. As with the Pioneer plaques, the Voyager records were created with the full awareness that the probability of their ever being found is extraordinarily small. The nearest star to our solar system, Proxima Centauri, is over 4 light-years away, and even at their impressive speeds of about 17 kilometers per second, the Voyager spacecraft would take tens of thousands of years to travel that distance. Moreover, they aren't heading toward any particular star, but simply away from the Sun in different directions. Voyager 1 is moving toward the constellation Ophiuchus and will pass within 1.6 light-years of the star Gliese, 725, in about 40,000 years. Voyager 2 is heading towards Sirius and will pass within 4.3 light-years of it in about 296,000 years. Given these trajectories and the vast emptiness of interstellar space, the odds against the Voyagers ever being found by another civilization are astronomical. Even if technologically advanced civilizations exist in our galaxy, space is simply too vast, and the Voyagers too small, for an accidental encounter to be likely. The Golden Records, like the Pioneer plaques before them, were created not with the expectation that they would actually be found, but as a symbolic gesture, a message in a bottle tossed into the cosmic ocean. This symbolic aspect of the interstellar messages was explicitly acknowledged by their creators. As Carl Sagan put it, the spacecraft will be encountered and the record played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. The act of creating and sending these messages was valuable in itself, regardless of whether they are ever received, as an expression of humanity's curiosity, creativity, and hope. The messages also served a more immediate purpose, encouraging people on Earth to think about how we might represent ourselves to beings utterly unlike us, and in doing so, to reflect on what is most essential and universal about human experience. The process of selecting the contents of the Voyager records prompted deep discussions about human values, achievements, and shortcomings. What music best represents the diversity of human artistic expression? What images capture the essence of human life and culture? What aspects of our existence might be comprehensible to beings with entirely different sensory systems and evolutionary histories? These questions have continued to inspire thought and discussion in the decades since the Voyager records were created. The messages have become cultural touchstones, referenced in books, films, music, and other media. They represent a kind of collective self-portrait of humanity, a deliberate attempt to distill the essence of our civilization into a form that could transcend not just cultural and linguistic barriers, but biological and temporal ones as well. The creation of the Voyager records also led to ongoing debate about the ethics and practicality of interstellar messaging. Some scientists have questioned whether it's wise to advertise our presence to unknown civilizations that might have technologies far beyond our own. Others have argued that any civilization capable of finding a tiny spacecraft in the vastness of interstellar space would already be so advanced that concerns about hostile intentions would be irrelevant. The discussion has expanded to encompass other forms of potential contact, including debates about whether we should actively broadcast messages to nearby stars in hopes of detection by other civilizations, a concept known as messaging extraterrestrial intelligence, or METI. Despite these debates, the precedent set by the Pioneer plaques and Voyager records has continued with subsequent deep space missions. New Horizons, launched in 2006 to explore Pluto and the Kuiper Belt, carries several cultural artifacts, including a small container with some of Pluto discoverer Clyde Tombaugh's ashes, a CD-ROM containing the names of over 400,000 people who signed up to send their names to Pluto, and a Florida state quarter and a United States postage stamp showing Pluto with the caption, "Not yet explored." While these items were not specifically designed as interstellar messages like the Pioneer plaques or Voyager records, they continue the tradition of including cultural and symbolic payloads on spacecraft that may eventually leave the solar system. New Horizons is currently traveling at about 14 kilometers per second, and after completing its extended mission to explore objects in the Kuiper Belt, will continue outward toward interstellar space, though it will not overtake the faster Voyager probes. The most recent addition to humanity's interstellar emissaries is the Parker Solar Probe, launched in 2018 to study the Sun's outer corona. Though its primary mission keeps it within the inner solar system, after completing its scientific objectives, the spacecraft's trajectory will eventually take it out of the solar system. It carries a memory card with the names of over 1.1 million people and a plate with a dedication to its namesake, solar physicist Eugene Parker, along with a copy of his seminal 1958 scientific paper on the solar wind. These various physical messages and artifacts represent just one aspect of humanity's legacy beyond Earth. Our robotic explorers themselves, as technological objects, tell their own story about the civilization that created them. Their design, construction, and the scientific instruments they carry reflect humanity's level of technological development, our understanding of physics and engineering, and our priorities in terms of what we consider worth studying and exploring. The Voyager spacecraft, for instance, with their nuclear power sources, communication systems capable of transmitting data across billions of kilometers, and diverse scientific instruments, represent a sophisticated understanding of nuclear physics, radio engineering, and planetary science. The very fact that they were designed to function for decades in the harsh environment of space, far from any possibility of repair or maintenance, demonstrates a high level of technological capability and long-term planning. Similarly, the trajectories of these spacecraft reflect humanity's understanding of celestial mechanics and our ability to calculate the complex gravitational interactions that enable gravity-assist maneuvers. The precise timing and positioning required to use a planet's gravity to alter a spacecraft's speed and direction, as both the Voyagers and New Horizons did with Jupiter, indicate a civilization with advanced mathematical and computational capabilities. For any civilization that might someday find one of our spacecraft, the object itself would provide significant information even without the intentional messages we've attached to them. The materials used in construction, the electronic components, the propulsion systems, all would offer clues about our technological development and resource utilization. Even the arrangement of instruments might suggest something about our sensory systems and what we consider important to measure and observe. Beyond the physical artifacts and the spacecraft themselves, humanity's legacy in space includes the electromagnetic signals we have been broadcasting for over a century. Radio and television transmissions, radar signals, and deliberate astronomical broadcasts have been radiating outward at the speed of light since the early 20th century, creating an ever-expanding bubble of human electromagnetic activity that now extends more than 100 light-years in all directions. Unlike the Voyager and Pioneer spacecraft, which travel relatively slowly and in specific directions, these electromagnetic signals propagate in all directions at the speed of light. The earliest radio broadcasts have already passed thousands of star systems, including many that we now know have planets in their habitable zones. If any technological civilizations exist within that 100 light-year radius, they might theoretically detect and possibly decode these signals, though in practice, the signals would be extremely faint at such distances and difficult to distinguish from natural radio sources unless the receiving civilization were specifically looking for them with very sensitive equipment. The content of these accidental transmissions, from early radio broadcasts to modern digital communications, provides a different kind of portrait of humanity than the carefully curated messages on the Pioneer and Voyager spacecraft. These signals contain our news and entertainment, our conflicts and celebrations, the mundane and extraordinary aspects of human life, all mixed together in a chaotic stream that would present significant challenges for any alien civilization attempting to make sense of them. There have also been several deliberate attempts to send radio messages to specific star systems thought to have potential for hosting life. The most famous of these was the Arecibo message, transmitted from the Arecibo radio telescope in Puerto Rico in 1974. This message, a binary pattern of 1,679 bits arranged in a 73 by 23 grid, was directed toward the globular star cluster Messier 13, about 25,000 light-years away. When arranged in the proper pattern, the bits form a pictorial message showing a stick-figure human, the DNA double helix, our solar system with Earth highlighted, the Arecibo telescope itself, and some basic mathematics and atomic numbers. More recently, various organizations and individuals have sent messages toward nearby stars, including the Teenage Message to Messier 13 in 2001, the Cosmic Call messages to several nearby Sun-like stars in 1999 and 2003, and the A message from Earth broadcast to the Gliese 581 system in 2008. These messages vary in content and complexity, but all represent deliberate attempts to announce our presence to potential extraterrestrial civilizations. Unlike the passive messages carried by spacecraft, these active radio transmissions have sparked significant debate within the scientific community. Some researchers have expressed concern about the wisdom of deliberately broadcasting our presence to unknown civilizations without broader discussion and consensus. Others argue that since we have already been unintentionally broadcasting our presence through radio and television signals for decades, deliberate messages don't meaningfully increase any hypothetical risk. All of these legacy elements, from physical artifacts on spacecraft to electromagnetic transmissions, share a common challenge: how to communicate across potentially unbridgeable gaps of biology, culture, and time. The creators of the Pioneer plaques and Voyager records struggled with this problem, attempting to ground their messages in universal physical constants and mathematical principles that any technological civilization would likely understand, regardless of their biological or cultural differences from humans. The Voyager records, for instance, use the hydrogen atom as a universal reference point. Since hydrogen is the most abundant element in the universe, and its physical properties would be known to any civilization capable of finding the spacecraft. The instructions for playing the record and decoding its images are based on these physical constants rather than on human language or cultural conventions. Similarly, the pulsar map uses the distinctive radio signatures of pulsars, which would be observable by any civilization with radio astronomy capabilities, to provide a cosmic address that could be understood across vast gulfs of time. Despite these ingenious efforts, true communication with beings utterly unlike ourselves would face enormous challenges. Even within our own species, communication across different languages and cultures can be difficult and prone to misunderstanding. How much greater would be the challenge of communicating with beings that evolved on a different world, possibly with different sensory systems, cognitive processes, and cultural frameworks? They might not recognize visual images or understand sound as we do. They might perceive aspects of reality that are entirely outside our sensory range. Their concepts of time, space, or causality might differ fundamentally from ours. These challenges of interstellar communication have been explored extensively in science fiction, from the linguistic puzzles of Arrival to the incomprehensible aliens of Stanislaw Lem's Solaris, the field of xenolinguistics, the hypothetical study of alien languages, attempts to imagine how we might establish communication with beings whose cognitive and sensory systems might be radically different from our own. Some researchers propose that mathematics and physics would provide the most likely common ground, since the physical laws of the universe are presumably the same everywhere and would be known to any technological civilization. The search for extraterrestrial intelligence, or SETI, has been grappling with these questions since the mid-20th century. Initially focused primarily on detecting radio signals from other civilizations, SETI has expanded to include searches for optical signals, artifacts, and other potential signatures of technological activity. The field approaches the question from the other direction, asking not how we might send messages to other civilizations, but how we might detect and decode messages sent by them. So far, despite decades of searching, SETI has not detected any confirmed signals from other civilizations. This negative result has led to discussions of the Fermi paradox, named after physicist Enrico Fermi, who asked in 1950, "Where is everybody?" The paradox notes that despite the vast size and age of the universe, which should provide ample opportunity for technological civilizations to arise and spread, we see no evidence of their existence. Numerous explanations have been proposed, from the rarity of life itself to the possibility that technological civilizations tend to destroy themselves or choose not to expand beyond their home planets. Whatever the answer to the Fermi paradox, the lack of detected extraterrestrial signals highlights the profound isolation of humanity in the cosmos, at least as far as we currently know. Our messages to the stars, whether carried by spacecraft or transmitted as radio signals, may never be received by other beings. They may be the unread diary entries of a solitary species, floating forever through the cosmic void. This possibility gives the Pioneer and Voyager messages a poignancy beyond their stated purpose as potential communications with other civilizations. They stand as humanity's attempt to transcend our isolation, to reach across the void to unknown others who may or may not exist. In this sense, they are as much an expression of hope and longing as they are practical attempts at communication. They also serve another purpose, one that their creators explicitly recognized, as time capsules of human civilization that might someday be the only evidence that we ever existed. In the distant future, billions of years from now, when the sun has expanded to become a red giant, engulfing the inner planets including Earth, and then contracted to a white dwarf, these spacecraft will still be traveling through the galaxy, bearing witness to a world and a species that are no more. Carl Sagan described the Voyager records as a symbolic statement of extraordinary significance, a way for humanity to say, "We were here, this is what we were like." In a universe where individual lives and even entire species and civilizations are ephemeral, these modest artifacts represent an attempt, however small, to leave a lasting mark on the cosmos, to extend human presence and memory beyond the lifespan of our species and our planet. This impulse to leave a legacy, to create something that outlasts us, is deeply human. From cave paintings to pyramids to written literature, humans have long sought ways to extend their influence beyond their own lifetimes. The Pioneer plaques and Voyager records represent the furthest extension of this impulse, potentially preserving a small fragment of human culture and technology for billions of years, long after Earth itself may have become uninhabitable. In this sense, these spacecraft and their messages stand alongside humanity's greatest artistic and cultural achievements as attempts to create meaning in the face of cosmic indifference and personal mortality. Like a symphony or a cathedral, they represent an investment of human creativity and resources in something that transcends immediate practical needs, something that reaches toward the eternal and universal. The messages also reflect a particular moment in human history, the late 20th century, when space exploration was still relatively new and the Cold War between the United States and Soviet Union dominated global politics. That such ambitious, optimistic, and peaceful messages were created during this period of geopolitical tension is remarkable in itself. The Voyager records, in particular, were consciously designed to represent all of humanity rather than just the United States, including music, images, and greetings from around the world. This inclusive universalist approach reflected a growing awareness in the late 20th century of humanity's shared fate and common heritage. The famous photograph known as Earthrise, taken by the Apollo 8 astronauts in 1968, showing Earth rising above the lunar horizon, had already begun to shift human perspective, emphasizing the fragility and unity of our planet against the backdrop of space. The Voyager records extended this perspective, presenting humanity as a single civilization rather than a collection of competing nations and cultures. In the decades since the launch of the Voyager spacecraft, our understanding of our place in the cosmos has continued to evolve. The discovery of thousands of exoplanets orbiting other stars has reinforced the likelihood that Earth is not unique as a potential abode for life. The recognition of the threat posed by climate change and other global environmental challenges has further emphasized humanity's shared fate and responsibility for our planetary home. And the development of powerful telescopes capable of directly imaging exoplanets promises to revolutionize our search for life beyond Earth in the coming decades. In this evolving context, the Pioneer and Voyager messages take on new significance. They stand as early expressions of a cosmic perspective that has become increasingly important to human self-understanding, a perspective that sees humanity as a single species on a small planet in a vast universe, rather than as competing tribes on a world without limits. They articulate a vision of humanity as curious, creative, and hopeful, capable of contemplating our place in the cosmos and reaching out to unknown others across the void. At the same time, these messages necessarily omit much of the complexity and contradiction of human existence. They do not dwell on war, injustice, environmental destruction, or the countless other ways in which human behavior falls short of our highest ideals. This curatorial choice was deliberate, a decision to present humanity at its best rather than to create a complete and balanced portrait that included our darkest aspects alongside our noblest achievements. Some critics have questioned this approach, suggesting that it presents an unrealistically sanitized version of human civilization. Carl Sagan defended the choice, arguing that a civilization capable of finding the Voyager spacecraft would already be far more advanced than humanity and would likely understand that the messages represent an idealized self-portrait rather than a complete depiction of human reality. As he put it, the record is a hopeful one. It says we were interested in what was beyond our little world, and we had the good sense not to destroy ourselves. This tension between honest representation and aspirational self-portrayal points to a deeper question about the purpose of these interstellar messages. Are they primarily attempts to communicate accurate information about humanity to potential extraterrestrial recipients? Or are they symbolic gestures, expressions of human hope and curiosity that are valuable regardless of whether they are ever received? The answer, as the creators themselves recognized, is that they are both, and the dual nature of their purpose shapes both their content and their significance. As the Voyager and Pioneer spacecraft continue their silent journeys through interstellar space, now joined by New Horizons and eventually by other missions, they carry these messages and questions with them. They bear witness to a moment in human history when we first reached beyond our solar system, when we began to understand our place in the cosmos and to contemplate the possibility of other minds with whom we might someday share our understanding of the universe. Whether or not these messages are ever received by other beings, they stand as testament to the human capacity for wonder, creativity, and hope. In a universe characterized by vastness, silence, and apparent indifference to human concerns, they represent our persistent attempt to create meaning, to establish connection, and to leave a legacy that transcends our brief moment in cosmic time. This legacy extends beyond the physical artifacts carried by our spacecraft. It includes the scientific knowledge gained from these missions, the inspiration they have provided to generations of scientists, engineers, artists, and dreamers, and the perspective they have given us on our own world. The famous pale blue dot photograph, taken by Voyager 1 in 1990 at the request of Carl Sagan, showing Earth as a tiny, faint pixel against the vastness of space, has become an iconic image that encapsulates both the insignificance of our planet on the cosmic scale and, paradoxically, the precious uniqueness of the only home we have known. In his reflection on this image, Sagan wrote words that have become some of the most quoted in the literature of space exploration. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives, the aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. This perspective, this cosmic humility, combined with a profound appreciation for the uniqueness of Earth and life, represents perhaps the most significant legacy of our deep space missions. It has influenced not only science but philosophy, art, literature, and popular culture, helping to shape a new understanding of humanity's place in the cosmos that transcends traditional religious and cultural frameworks. As we contemplate the future of human space exploration and possible interstellar missions, this legacy provides both inspiration and guidance. It reminds us of the value of curiosity and wonder, of the importance of seeing beyond our immediate concerns to the larger context of cosmic time and space. It encourages us to approach the unknown with humility, creativity, and hope rather than fear or arrogance. And it challenges us to consider not just what we might discover beyond Earth, but what kind of presence we wish to establish in the broader cosmos. The Pioneer plaques and Voyager records, those modest artifacts carrying humanity's first deliberate messages to the stars, continue to inspire new generations of scientists, artists, and thinkers to consider these questions. As we expand our presence in the solar system and perhaps someday beyond, we carry with us the legacy of these early missions, their scientific achievements, their cultural significance, and their profound embodiment of the human desire to reach beyond ourselves, to understand our place in the cosmos, and to leave a mark that outlasts our brief moment in the vast expanse of cosmic time. In the silent, cold darkness of interstellar space, far beyond the planets, our spacecraft continue their journeys, bearing these messages from a curious species on a small blue planet, a species that looked up at the night sky and wondered what might lie beyond, that built machines to extend its reach across distances too vast for biological travel, that imagined unknown others with whom it might someday share its understanding of the universe. Whatever the ultimate fate of these missions and messages, they stand as testament to the human capacity for wonder, creativity, and hope in the face of cosmic vastness and silence. As we drift towards sleep, let us imagine these tiny emissaries of Earth, now so far away that even their radio signals, traveling at the speed of light, take many hours to reach us. Let us picture the golden records, those time capsules of human culture, still intact after decades in the harsh environment of space, protected by their aluminum cases as they journey onward. Let us consider that long after we are gone, long after Earth itself may have become uninhabitable as the sun expands in its red giant phase billions of years from now, these modest artifacts will continue their silent flight through the galaxy, carrying with them the echo of a civilization that once existed on a small planet, orbiting an ordinary star in one arm of a spiral galaxy, a civilization that wondered about its place in the cosmos and reached out, however tentatively, toward the stars. Perhaps, against all odds, they will someday be found by beings utterly unlike ourselves, beings who evolved on a different world around a different star. Perhaps these unknown others will decipher the pulsar map and locate our solar system, will figure out how to play the golden records and see the images, and hear the sounds of Earth as it was in the late 20th century. Perhaps they will wonder about the strange beings who sent these messages, their nature, their history, their fate. Or perhaps, more likely, the spacecraft will journey forever through the void, undetected, their messages unread, silent ambassadors of a world that once was. Either way, the very existence of these messages, and the hope and curiosity they embody, tell us something important about ourselves. In a universe that often seems indifferent to human concerns, In the face of cosmic scales of time and distance that dwarf our individual lives, and even our species' existence, we continue to create, to reach outward, to seek connection and meaning. The Voyager and Pioneer messages, perhaps the longest-lasting artifacts our civilization will ever create, stand as testament to this distinctly human quality, this persistent hope that somewhere, sometime, someone might receive our message in a bottle, cast into the vast cosmic ocean. As our first emissaries to the stars continue their silent journeys through interstellar space, humanity looks toward the next phase of deep space exploration. The Voyagers, Pioneers, and New Horizons have shown us the way, but they represent only the beginning of our reach beyond the solar system. The journey beyond our solar system presents challenges far greater than any previous space mission. The vast distances involved, the limitations of current propulsion systems, the difficulties of communication across light years of space, and the need for spacecraft that can function reliably for decades or even centuries without maintenance, all push the boundaries of our technological capabilities. Yet the scientific rewards of such missions would be enormous, potentially transforming our understanding of the interstellar medium, the structure of our galaxy, and perhaps even the prevalence of life beyond Earth. One of the most significant challenges for future interstellar missions is propulsion. The Voyager spacecraft, traveling at about 17 kilometers per second, would take more than 70,000 years to reach the nearest star system, Alpha Centauri. To make interstellar exploration practical within human lifetimes, far higher velocities are needed. Several advanced propulsion concepts are under active research and development. Nuclear propulsion, which uses the energy released by nuclear reactions to heat a propellant or directly generate thrust, could potentially achieve speeds several times greater than conventional chemical rockets. More advanced concepts like nuclear pulse propulsion could theoretically achieve speeds of several % of the speed of light. Another promising approach is solar or laser sail technology, where large, lightweight reflective sails are propelled by the pressure of sunlight or a powerful laser beam. The Breakthrough Starshot initiative, announced in 2016, aims to develop tiny spacecraft with light sails that could be accelerated to 20% of the speed of light by ground-based lasers, potentially reaching Alpha Centauri in just 20 years. Other exotic propulsion concepts include fusion rockets, antimatter engines, and various electromagnetic and plasma-based systems. While many of these technologies remain speculative or in early stages of development, they represent potential paths to true interstellar travel within the constraints of known physics. Beyond propulsion, future interstellar missions will need to overcome numerous other challenges. Power generation over decades or centuries of flight would likely require advanced radioisotope systems or small nuclear reactors. Communications across interstellar distances would need high-power transmitters and extremely sensitive receivers to maintain contact with Earth. Navigation systems would need unprecedented precision to target distant stars and planets, and onboard computers and scientific instruments would need to function reliably for many decades without maintenance. Despite these challenges, several concrete proposals for interstellar precursor missions have been developed by space agencies and private organizations. These missions, while not necessarily targeting other star systems directly, would venture far beyond the current reach of our spacecraft, exploring the outer edges of the solar system and potentially the nearby interstellar medium. One such concept is the Interstellar Probe, studied by NASA and other space agencies, which would travel to a distance of 1,000 astronomical units from the Sun, more than 3 times farther than Voyager 1's current position. At this distance, the probe could perform direct measurements of the pristine interstellar medium and could use the Sun as a gravitational lens to achieve unprecedented resolution in observations of distant objects. Such a mission could potentially be launched in the 2030s, reaching its target distance within about 50 years. For missions targeting actual interstellar destinations, the Breakthrough Starshot initiative represents perhaps the most developed current proposal. This project aims to develop a fleet of centimeter-sized spacecraft, each equipped with a light sail, sensors, and communication equipment. These tiny probes would be accelerated to 20% of the speed of light by a ground-based laser array, allowing them to reach Alpha Centauri in approximately 20 years. Each probe would carry minimal instrumentation due to its small size, but by launching thousands of them, the mission could ensure that at least some reach the target and return useful data. Other approaches to interstellar exploration emphasize larger, more capable spacecraft that would take longer to reach their destinations, but could perform more comprehensive investigations upon arrival. Organizations like the British Interplanetary Society have developed detailed concepts for robotic interstellar probes, including the famous Project Daedalus from the 1970s and its more recent successor, Project Icarus, which envision large fusion-powered spacecraft capable of reaching nearby stars within a century of launch. One of the most fascinating targets for future interstellar missions is the Proxima Centauri system, particularly its planet Proxima Centauri b, discovered in 2016. This planet orbits within the habitable zone of its host star, a small red dwarf that is part of the Alpha Centauri triple star system and is our Sun's nearest stellar neighbor at just 4.2 light-years away. While we know little about this world beyond its approximate size and orbital parameters, it represents the closest, potentially habitable exoplanet to Earth, making it a compelling destination for future exploration. Imaging Proxima Centauri b from Earth or Earth orbit is extremely challenging due to its proximity to its much brighter host star. A spacecraft sent to the Proxima Centauri system, however, could potentially obtain detailed images and spectroscopic data, revealing the planet's surface features, atmospheric composition, and potential signs of habitability or even life. Beyond the nearest stars, our galaxy contains hundreds of billions of other star systems, many of which likely host planets of their own. Recent surveys suggest that planets are common throughout the Milky Way, with a significant fraction potentially residing in the habitable zones of their host stars. While missions to these more distant systems would face even greater challenges than those targeting nearby stars, they represent the long-term frontier of human exploration. Private initiatives are also playing an increasingly important role in deep space exploration. Beyond the Breakthrough Starshot project mentioned earlier, companies and non-profit organizations are developing technologies and mission concepts that could contribute to future interstellar efforts. SpaceX's development of large, reusable launch vehicles could dramatically reduce the cost of placing massive payloads into orbit, a crucial first step for any interstellar mission that requires significant infrastructure in space. And various smaller companies and research groups are working on specific technologies relevant to interstellar travel, from advanced propulsion systems to long-duration power sources to resilient electronics. One interesting approach to interstellar exploration that combines both technical and social innovation is the concept of a world ship or generation ship. Rather than attempting to reach other stars within a human lifetime, these hypothetical vessels would carry entire communities of people on journeys lasting centuries or millennia. The passengers who embarked would not live to see the destination, but their descendants would carry on the mission, eventually arriving at another star system. While such concepts remain firmly in the realm of science fiction for now, they represent a different approach to the timescale problem of interstellar travel. More near-term concepts include hibernation or suspended animation technologies that might allow human travelers to survive lengthy journeys in a state of reduced metabolic activity. These biological approaches to the challenge of interstellar travel highlight the interdisciplinary nature of the problem, which involves not just physics and engineering but biology, medicine, psychology, and sociology. For all the attention given to human interstellar travel, however, it is likely that the first missions to other stars will be robotic, following in the tradition of the Voyager and Pioneer spacecraft, but with far greater capability and speed. Advanced artificial intelligence might allow these robotic explorers to operate with significant autonomy, making complex decisions without waiting for instructions from Earth that would take years to arrive at interstellar distances. The development of self-replicating robotic systems represents a particularly powerful approach to galactic exploration. A spacecraft capable of using local resources to create copies of itself could potentially explore the entire galaxy over millions of years, even if each individual probe could only reach the nearest stars. While such technology is far beyond our current capabilities, it represents a logical extension of ongoing developments in artificial intelligence, robotics, and in situ resource utilization. As we contemplate these various approaches to interstellar exploration, we must also consider the ethical dimensions of extending human presence beyond our solar system. What responsibilities do we have when exploring other star systems that might harbor life of their own? How do we ensure that our probes don't contaminate pristine environments? These questions have been explored in science fiction for decades, but as the technical barriers to interstellar travel gradually diminish, they become increasingly relevant to real-world planning and policy. In considering future interstellar missions, we must also acknowledge the vast expanse of the unknown that lies between our current capabilities and true interstellar travel. The history of space exploration is filled with surprise discoveries and unexpected challenges. As we venture into the space between stars, we will certainly encounter phenomena that we have not predicted or prepared for, requiring creativity, adaptability, and a spirit of exploration that goes beyond detailed technical planning. This spirit of exploration, the drive to see what lies beyond the next horizon, has been a constant through human history. From the first seafarers who ventured beyond sight of land to the astronauts who left footprints on the moon, the interstellar frontier represents the ultimate expression of this impulse, a boundless expanse that will challenge human ingenuity and determination for generations to come. Our future interstellar explorers will build on the legacy of the voyagers and pioneers, carrying forward the human impulse to explore, discover, and understand. They will venture to nearby stars, potentially discovering new planets with conditions unlike anything in our solar system. They will sample the interstellar medium directly, measuring its composition, structure, and dynamics with unprecedented precision. And perhaps, someday, they might even discover evidence of life beyond Earth, transforming our understanding of biology and of our place in the cosmos. The road to these discoveries will be long and challenging, requiring sustained effort across multiple generations and the development of technologies that now exist only as theoretical concepts or laboratory demonstrations. Yet the history of space exploration suggests that such challenges can be overcome through a combination of scientific insight, engineering creativity, institutional commitment, and public support. As we conclude this exploration of future interstellar missions, let us return to the fundamental question of why this endeavor matters. Why should we invest resources, creativity, and effort in reaching toward other stars when so many challenges remain here on Earth? The answers are many and interconnected. At the most practical level, the technologies developed for interstellar travel would have numerous applications on Earth. At a scientific level, interstellar missions would provide unprecedented insights into the nature of other star systems and potentially the existence of extraterrestrial life. At a philosophical level, interstellar exploration represents the ultimate expression of the human drive to explore, discover, and understand. And at an existential level, expanding beyond our solar system offers a form of long-term insurance for human civilization and Earth life more broadly. As we drift towards sleep, let us imagine the future spacecraft that will follow in the wake of the voyagers and pioneers, venturing beyond the boundaries of our solar system into the true depths of interstellar space. In the silent darkness between the stars, these spacecraft will represent the farthest extension of human capability and vision, tiny beacons of intention and purpose in the vast, indifferent void, and use the sun as a gravitational lens for unprecedented astronomical observations. The Breakthrough Starshot initiative, as mentioned earlier, takes a more radical approach, aiming to develop gram-scale spacecraft with light sails that could be accelerated to 20% of the speed of light by ground-based lasers, reaching Alpha Centauri within about 20 years of launch. This project has received significant funding and has begun technology development efforts focused on the key challenges, including the design of the tiny spacecraft, the development of the powerful laser array needed for acceleration, and the creation of communication systems that could transmit data across interstellar distances. Various other organizations and research groups are working on specific technologies relevant to interstellar travel, from advanced nuclear propulsion concepts to long-duration power systems, to materials that could withstand the harsh conditions of interstellar space. These efforts, while not full mission proposals, contribute to the gradual accumulation of capabilities that will eventually enable true interstellar exploration. In the meantime, our existing interstellar ambassadors, the Voyager and Pioneer spacecraft, continue their journeys outward. Voyager 1, the most distant human-made object, is now over 23 billion kilometers from Earth. having crossed the heliopause in 2012 to become the first spacecraft to enter interstellar space. Its instruments continue to return valuable data about this previously unexplored region, though its power supply is gradually diminishing and some systems have been shut down to conserve energy. Engineers estimate that the last scientific instrument will likely be turned off around 2025, after which the spacecraft will continue its silent journey with no further communication with Earth. Voyager 2, which followed its twin into interstellar space in 2018, faces similar power constraints but continues to function, providing complementary data from a different region of the interstellar medium. The Pioneer spacecraft, meanwhile, have already fallen silent. Pioneer 11's last transmission was received in 1995, and Pioneer 10's in 2003. Yet they too continue their physical journeys, bearing their engraved plaques as perhaps the longest-lasting artifacts of human civilization. New Horizons, having completed its historic flyby of Pluto in 2015 and its encounter with the Kuiper Belt object Arrokoth in 2019, continues to function and may have the opportunity to observe additional distant objects as it follows a trajectory that will eventually take it beyond the solar system. Though it is traveling more slowly than the Voyagers and will not overtake them, it represents a more modern interstellar precursor with more advanced instruments and capabilities. These existing missions, while not designed primarily as interstellar probes, provide valuable experience and data that will inform future dedicated efforts. They demonstrate the remarkable durability of properly designed spacecraft, the challenges of communication across vast distances, and the surprising discoveries that await in the vast realm beyond the planets. They also serve as technological milestones, points of reference for how far we have come and how far we have yet to go in our quest to explore beyond the solar system. As we contemplate the future of interstellar exploration, we must also consider the broader context of space development and utilization. Establishing a robust human presence throughout the solar system, from the Moon and Mars to the asteroid belt and the moons of the outer planets, would provide a much stronger foundation for eventual interstellar efforts. The resources, infrastructure, and experience gained from solar system colonization would enable more ambitious projects than could be supported from Earth alone. Particularly for concepts like world ships or large fusion-powered spacecraft, construction and launch from Earth would be prohibitively difficult, but might become feasible from a solar system-wide civilization, with access to the vast resources of the asteroids, comets, and gas giants. The development of closed-loop life support systems, efficient resource utilization technologies, and sustainable habitats for space settlement would also have direct applications to long-duration interstellar missions. A civilization capable of maintaining viable habitats in the cold, radiation-filled environment of the outer solar system would be much better prepared for the challenges of interstellar travel than one confined to Earth or even to the inner planets. The economic and industrial capacity of a solar system spanning civilization would likewise enable projects of scale and complexity far beyond what could be supported by Earth's limited resources alone. In this sense, interstellar exploration represents not an alternative to solar system development, but its logical extension, the next frontier that becomes accessible once humanity has established a secure, sustainable presence throughout our home system. The technologies, resources, and organizational structures needed for meaningful interstellar exploration would likely emerge organically from a successful expansion throughout the solar system, just as the capabilities for space exploration itself emerged from the industrial and technological development of Earth-bound society. This perspective suggests a natural progression of human expansion, from Earth to orbit, to the Moon and Mars, then to the asteroids and outer planets, and eventually to the stars. Each step builds upon the previous ones, extending human reach and capability, while developing the technologies and resources needed for the next phase. While visionaries might focus on the ultimate goal of reaching other stars, the practical path to achieving that goal likely involves a gradual, sustained expansion of human presence and capability throughout our own solar system. That said, certain aspects of interstellar exploration can and should proceed in parallel with solar system development. Scientific studies of the interstellar medium, astronomical observations of nearby star systems, research into advanced propulsion concepts, and the development of technologies for long-duration spacecraft operation can all advance without waiting for full solar system colonization. The breakthrough Starshot concept, with its emphasis on small, laser-accelerated probes rather than massive crewed vessels, might be achievable with near-term technology deployed from Earth, providing an early pathway to interstellar exploration, even as the broader human expansion into the solar system continues. This parallel development reflects the complementary roles of science and settlement in space exploration. Scientific missions can venture far beyond the frontier of human settlement, returning knowledge that informs and guides subsequent expansion. Settlement, in turn, provides the resource base and industrial capability for more ambitious scientific exploration, creating a positive feedback loop that drives both facets of space development forward. Interstellar science missions might begin while human settlement is still limited to the inner solar system, but truly ambitious interstellar projects, especially those involving human travel, would likely require the resources and capabilities of a civilization spanning multiple worlds. As we envision this future of solar system development and interstellar exploration, we must also consider the timescales involved. The expansion of human presence throughout the solar system will likely unfold over centuries, and even the most optimistic scenarios for interstellar travel involve missions lasting decades or centuries. These timescales far exceed the planning horizons of most human institutions, from corporations to governments, which typically focus on outcomes achievable within years or decades at most. This mismatch between the timescales of interstellar exploration and those of conventional planning creates a significant challenge for organizing and sustaining the necessary efforts. How do we maintain focus and commitment to goals that may not be achieved within a human lifetime? How do we design institutions and funding mechanisms that can persist across generations? How do we ensure that knowledge, expertise, and purpose are transmitted effectively to future participants in these long-term projects? These questions have no simple answers, but historical examples of long-duration human endeavors provide some guidance. Religious institutions have maintained consistent purposes and practices across many centuries. Some architectural projects, like medieval cathedrals, span generations from conception to completion. Scientific traditions have preserved and expanded knowledge across centuries of systematic inquiry. These precedents suggest that with appropriate cultural frameworks, institutional designs, and transmission mechanisms, humans can indeed organize and sustain efforts that transcend individual lifetimes. For interstellar exploration specifically, one approach might involve embedding these long-term goals within broader cultural and scientific traditions that provide both immediate benefits and gradual progress toward the ultimate objective. A program of solar system exploration and development, for instance, could produce valuable scientific knowledge, resource utilization capabilities, and settlement opportunities in the near term, while also building the foundation for eventual interstellar missions. The technologies developed for exploring the outer solar system would have direct applications to interstellar precursor missions, creating a natural progression that maintains momentum while working toward distant goals. Another approach involves designing institutional structures specifically for long-term persistence and mission continuity. The Long Now Foundation, for instance, was established to foster long-term thinking and responsibility, with projects like the 10,000-year clock intended to tangibly represent timescales beyond normal human consideration. Similar institutions focused on interstellar exploration might employ a variety of mechanisms for maintaining commitment across generations, from endowments and legal frameworks to cultural practices and educational initiatives that transmit both technical knowledge and sense of purpose to future participants. The involvement of multiple independent organizations, from national space agencies to private foundations to academic institutions, also provides a form of redundancy that helps ensure continuity, despite the potential failure or changing priorities of any individual entity. If the pursuit of interstellar exploration becomes embedded in a diverse ecosystem of organizations and initiatives, it becomes more resilient to political, economic, and social changes that might otherwise derail such long-term efforts. Ultimately, the future of interstellar exploration depends not just on overcoming technical challenges, but on developing social and institutional innovations that can sustain complex, collaborative endeavors across timescales far exceeding individual human lives. This may prove to be as difficult and as crucial as developing the propulsion systems, power sources, and life support technologies needed for the physical journey to the stars. As we conclude this exploration of future interstellar missions and the next frontier of space exploration, let us return to the fundamental question of why this endeavor matters. Why should we invest resources, creativity, and effort in reaching toward other stars when so many challenges remain here on Earth? What value does interstellar exploration offer to a civilization still grappling with poverty, inequality, environmental degradation, and conflict? The answers are many and interconnected. At the most practical level, the technologies developed for interstellar travel, from advanced propulsion and energy systems to closed-loop life support and autonomous robotics, would have numerous applications on Earth, potentially addressing some of our most pressing problems. The history of space exploration demonstrates this pattern of beneficial spin-offs, from satellite communications and weather prediction to medical imaging and materials science advances. At a scientific level, interstellar missions would provide unprecedented insights into the nature of other star systems, the formation and evolution of planets, the dynamics of interstellar space, and potentially even the existence and characteristics of extraterrestrial life. These discoveries would transform our understanding of the universe and our place within it, potentially answering some of the most profound questions that humans have asked throughout our history. Are we alone? How common are worlds like Earth? What is the long-term fate of planetary systems like our own? At a philosophical level, interstellar exploration represents the ultimate expression of the human drive to explore, discover, and understand, a fundamental aspect of our nature that has propelled us from our African origins to every corner of the Earth and now beyond. This impulse has been a powerful force for human development and achievement throughout our history, driving not just geographical exploration but scientific inquiry, technological innovation, and artistic creativity. The stars represent the greatest frontier we can currently conceive, a boundless realm of potential discovery that can inspire and challenge humanity for countless generations to come. And at an existential level, expanding beyond our solar system offers a form of long-term insurance for human civilization and Earth life more broadly. A species confined to a single planet remains vulnerable to extinction from various cosmic catastrophes, from asteroid impacts to nearby supernovae, to the eventual death of our Sun. By establishing a presence around other stars, humanity would create a kind of redundancy that could ensure our long-term survival, regardless of what befalls Earth or the solar system. The same argument applies to Earth life more generally, whose remarkable diversity and 4 billion-year evolutionary heritage could be preserved and extended through human settlement of other star systems. These various motivations, from the practical to the philosophical to the existential, combine to make a compelling case for pursuing interstellar exploration, not as an alternative to addressing Earth's problems, but as a complementary endeavor that expands our capabilities, knowledge, and perspective. The challenges are immense, the timescales daunting, and the uncertainties numerous, but the potential rewards, both tangible and intangible, are equally vast. As we drift towards sleep, let us imagine the future spacecraft that will follow in the wake of the Voyagers and Pioneers, venturing beyond the boundaries of our solar system into the true depths of interstellar space. Perhaps they will be tiny light-sail craft racing at a significant fraction of the speed of light, or massive fusion-powered vessels carrying scientific instruments of unprecedented sensitivity, or self-replicating probes designed to explore the galaxy over cosmic timescales. Whatever form they take, these emissaries will extend human presence and awareness far beyond our current frontier, carrying forward the ancient human impulse to see what lies beyond the next horizon, to understand our place in the cosmos, and to reach toward the unknown with curiosity, creativity, and hope. In the silent darkness between the stars, these spacecraft will represent the farthest extension of human capability and vision, tiny beacons of intention and purpose in the vast, indifferent void. And in their silent journeys through interstellar space, they will embody not just technological achievement, but the enduring human capacity for wonder, for ambition that transcends the immediate and the practical, for imagining possibilities that lie beyond current limits, and then devising ways to transform those possibilities into reality. This, perhaps, is the greatest value of interstellar exploration. Not just what we might discover among the stars, but what such voyages reveal about ourselves and what we are capable of achieving when motivated by curiosity, courage, and a vision that extends beyond the boundaries of our birth world toward the infinite frontier that lies beyond. In the vast expanse of space, distance and time take on new meanings. The spacecraft we have sent to the outer reaches of our solar system and beyond travel through regions where the familiar markers of human experience no longer apply. There are no days or nights, no seasons, no weather, no landmarks to measure progress. There is only the endless void, punctuated by the distant stars, and the steady passage of time measured in years, decades, and eventually, centuries. Consider the journey of Voyager 1, now the most distant human-made object in the universe. Launched in 1977, it has been traveling for nearly half a century. The radio signals it sends back to Earth, moving at the speed of light, take over 20 hours to reach us. By the time we receive a message from Voyager, it has already moved thousands of kilometers farther into the void. Our communication with it occurs across a gulf of both space and time, a conversation stretched by the fundamental limits of physics. The distances involved in space exploration challenge our intuition. Voyager 1 is currently over 23 billion kilometers from Earth, a number so large it becomes difficult to comprehend. To put this in perspective, if the distance from Earth to the Sun, 149 million kilometers, were reduced to the length of one footstep, Voyager would now be over 150 steps away. Yet even at this incredible distance, Voyager has traveled only 0.002 light-years, a tiny fraction of the 4.2 light-years to the nearest star. These vast distances create a poignant asymmetry in our relationship with our distant explorers. When we send a command to Voyager, the scientists who issued the instruction must wait nearly 2 days to learn whether it was successfully received and executed. The spacecraft experiences the command instantly upon reception, but for the humans who sent it, a significant portion of a lifetime might pass before the final results of a complex series of instructions are known. This delay challenges our normal modes of interaction and control, forcing a kind of patience and foresight that few other human activities require. Time itself behaves differently in the context of deep space missions. The spacecraft we send on these journeys must function reliably for decades, far longer than most human artifacts are designed to last. The Voyager spacecraft were originally designed for 5-year missions, yet they have continued to operate for over 45 years. New Horizons, which visited Pluto in 2015, may still be returning data from the outer solar system in the 2030s, more than 25 years after its launch. These timescales stretch the boundaries of human planning and institutional continuity. The scientists and engineers who designed these missions often do not live to see their completion. The student who begins working on an interstellar mission concept today might be retired or deceased before the spacecraft reaches its destination. This creates a kind of intergenerational relay, where the torch of knowledge and purpose must be passed from one group of humans to the next over the course of a single mission. It requires a perspective that transcends individual careers and lifespans, a willingness to begin something that others will need to complete. This relationship with time extends to the spacecraft themselves. The electronic components, scientific instruments, and mechanical systems aboard our deep space explorers experience time in a way profoundly different from similar systems on Earth. In the cold, radiation-filled environment of deep space, far from the possibility of human intervention or repair, these systems age and evolve in unique ways. Some components fail entirely, others degrade gradually, and still others continue to function decades after their expected lifetimes. The spacecraft themselves become time capsules of the era in which they were built, carrying 1970s or early 2000s technology into a future where such systems have long since become obsolete on Earth. There is a certain melancholy in contemplating the fate of these distant emissaries. Eventually, the radioisotope power sources aboard the Voyagers and New Horizons will decay to the point where they can no longer generate enough electricity to power even the most basic systems. The spacecraft will fall silent, though they will continue their physical journeys through space. Voyager 1 is expected to maintain power until approximately 2025, after which it will no longer be able to communicate with Earth. It will become a ghost ship, carrying its golden record through interstellar space for millions or even billions of years, long after Earth itself has changed beyond recognition. This silent future underscores the patience required by deep space exploration. The Voyagers will pass within a few light years of various stars over the next several 100,000 years. Pioneer 10 will pass near Aldebaran in about 2 million years. These timescales dwarf not just individual human lifespans, but the entire recorded history of human civilization, which stretches back only about 5,000 years. They approach the timescales of geological processes and evolutionary change, connecting human actions in the present to a deep future we can barely imagine. In sending these spacecraft beyond our solar system, we engage with time in a way that few other human activities allow. We create artifacts explicitly designed to outlast our civilization, perhaps even our species. The Pioneer plaques and Voyager golden records were created with the understanding that they might someday be the only evidence that humanity ever existed. They represent an attempt to extend human presence and memory beyond the expected lifetime of Earth as a habitable world, a reaching toward a kind of immortality, however tenuous. This engagement with deep time reflects a growing awareness of our place in cosmic history. Earth formed about 4.5 billion years ago. Life appeared within the first billion years of Earth's existence and has continued uninterrupted since then, a chain of genetic information extending across vast spans of time. Human beings, as a distinct species, have existed for only about 300,000 years, a mere moment in geological time. Our technological civilization is younger still, only a few thousand years old. Yet in this brief window, we have developed the capability to send our artifacts beyond the solar system, potentially extending the reach of humanity's influence far beyond the lifetime of our species, or even our planet. The cosmic perspective offered by these distant missions also provides a unique vantage point from which to view Earth itself. The famous pale blue dot photograph, taken by Voyager 1 in 1990 at the request of Carl Sagan, shows our planet as a tiny, faint pixel against the vastness of space. From a distance of 6 billion kilometers, all of human history, all our achievements and conflicts, our entire existence, is contained within that single point of light. As Sagan eloquently noted, this image reveals both our insignificance in the cosmic scale and, paradoxically, the precious uniqueness of our world. This perspective has profound implications for how we understand time on human scales. The daily concerns that occupy most of our attention, the urgent issues that seem so pressing in the moment, take on a different significance when viewed against the backdrop of cosmic time. Political systems rise and fall, societies transform, technologies advance and become obsolete, all within time frames that register as mere instants from the perspective of our distant spacecraft. Yet there is also a kind of wonder in this disparity of scales. The same brief window of human existence that appears so insignificant from a cosmic perspective has also produced music, literature, art, science, and philosophy. It has given rise to creatures capable of contemplating their own place in the universe, of sending their machines and messages beyond their world, of imagining futures they will not live to see. If the brevity of human civilization in cosmic time reveals our insignificance, the depth and richness of human experience within that brief window reveals something equally profound about the capacity of consciousness to create meaning, even in a universe indifferent to our existence. The spacecraft themselves embody this duality. They are, on one hand, tiny specks of metal and silicon adrift in the immensity of space, their mass and energy negligible against the cosmic backdrop. Yet they are also the product of thousands of years of accumulated human knowledge, the physical embodiment of our understanding of physics, engineering, mathematics, and countless other disciplines. They represent the current pinnacle of our technological achievement, carrying our presence, however small, into regions no living thing from Earth has ever experienced directly. As these spacecraft journey outward, they also journey forward in time, becoming progressively more ancient from the perspective of Earth, while continuing to exist in their own present. A signal received from Voyager today was sent more than 20 hours ago, from a spacecraft designed and built nearly 50 years in our past. This layering of timescales, This simultaneous engagement with past, present, and future is unique to deep space exploration and offers a perspective on time unavailable in other human endeavors. The patience required for these missions also stands in stark contrast to the accelerating pace of modern human society. In an era of instant communication, rapid technological change, and constant demands for immediate results, the decades-long timeframes of deep space missions represent a different mode of engagement with time and progress. They remind us that some achievements require sustained effort across generations, that there is value in beginning projects whose completion we may not live to see. This perspective may be one of the most important legacies of our distant explorers. In a world increasingly focused on short-term results and immediate gratification, they demonstrate the possibility and value of long-term thinking and planning. They encourage us to consider our responsibilities not just to the present, but to future generations, to recognize that our actions today create the world of tomorrow, even if we will not be there to witness it. As we contemplate the silent journeys of our spacecraft through the depths of space and time, we might also reflect on our own relationship with these dimensions. Human lives are brief compared to cosmic timescales, our direct experience limited to a tiny region of the universe. Yet through science, art, and imagination, we extend our awareness far beyond these limitations. We contemplate the birth of the universe 13.8 billion years ago and its possible end trillions of years in the future. We study galaxies billions of light years distant, whose light began its journey toward Earth before our planet even existed. We send our robotic emissaries beyond the solar system, knowing they will continue their journeys long after we are gone. In doing so, we transcend, if only partially and temporarily, the fundamental constraints of human existence. We become more than creatures bound to a particular time and place, more than brief participants in the ongoing story of the cosmos. We become observers and explorers of that story, capable of understanding our own role within it and imagining its continuation beyond our individual or even collective lifespans. The spacecraft that now drift through the outer reaches of our solar system and beyond embody this transcendence. They are simultaneously monuments to what humanity has already achieved and pioneers of what we might yet discover. They connect our present to both the deep past from which we emerged and the deep future toward which we send our messages and artifacts. They remind us that though individual lives are brief and civilizations fragile, the ripples of our actions can extend far beyond our immediate experience, touching times and places we will never know directly. As we drift toward sleep, let us contemplate these silent travelers, moving ever outward through the darkness between the stars. Let us imagine the enormous gulfs of time and space through which they journey, carrying with them the echo of a species that looked up at the night sky and wondered what might lie beyond, that reached outward with its machines and its mathematics to touch the edge of the cosmic ocean. And let us recognize in their patient journeys a kind of poem written in metal and radiation, in trajectory and telemetry, a testament to the human capacity to transcend its limitations through creativity, cooperation, and an unwavering curiosity about the universe and our place within it. In the quiet hours of mission control, when most of the world sleeps, a small team of engineers and scientists sits in vigilant attention, listening for the faintest of whispers from the edge of our solar system and beyond. The signals they await travel across billions of kilometers of empty space, electromagnetic messengers from our most distant explorers. These signals, by the time they reach Earth, are incredibly faint, their power measured in billionths of a watt, a whisper so subtle that only the most sensitive receivers on our planet can detect them. The Deep Space Network, a global array of massive radio antennas in California, Spain, and Australia, stands ready to capture these delicate communications. The largest antennas, 70 meters in diameter, are aimed with exquisite precision at points in space where our distant spacecraft should be, tracking their predicted positions across the sky. When a signal is received, a moment of connection is established across the vast gulf of space, a tenuous link between humanity and its farthest mechanical explorers. What do these distant voices tell us? Their primary messages are technical telemetry, data about the spacecraft's health and orientation, power levels, and temperature readings, the status of scientific instruments. This information, encoded in radio waves, allows engineers to monitor the condition of machines they can never repair or even see again with human eyes. It's a distant doctor-patient relationship, conducted across billions of kilometers, where diagnosis must be made without direct examination, and treatments consist entirely of carefully crafted instructions sent into the void. The scientific data these spacecraft return is equally precious. Measurements of magnetic fields, counts of cosmic ray particles, analyses of interstellar dust, all provide unique insights into environments no human has ever visited. Each bit of information, carefully encoded and transmitted across the immense distances, adds another piece to our understanding of the universe beyond our solar system. Like explorers sending maps back from uncharted territories, these spacecraft sketch the contours of regions previously known only through remote observation or theoretical prediction. The time it takes for these signals to cross the enormous distances creates a curious asynchronicity in our communication. When we receive a transmission from Voyager 1, we are hearing its voice from 20 hours ago. When we send a command, it won't be received until nearly a day later. This delay enforces a kind of cosmic patience, a recognition that our relationship with these distant explorers cannot operate on human timescales, but must adapt to the fundamental constraints imposed by the speed of light and the immensity of space. This patience extends to the gradual fading of these distant voices. The radioisotope power sources that provide electricity to the Voyager spacecraft are slowly decaying, providing less power with each passing year. Engineers have responded by selectively turning off systems and instruments, prioritizing those most essential for communication and the most valuable for science. It's a kind of triage conducted across interstellar distances, a careful management of dwindling resources to extend the missions as long as possible. Eventually, perhaps around 2025, the power will drop below the critical threshold needed to operate the radio transmitters. At that point, the Voyagers will fall silent, though they will continue their physical journeys through interstellar space. This approaching silence lends a poignancy to each communication, a reminder that we are witnessing the final chapters of missions that have extended far beyond their planned durations and expectations. The Voyager spacecraft, in particular, occupy a unique place in the annals of exploration. They are the first and so far only human-made objects to leave our solar system and enter interstellar space. They have crossed a boundary that, throughout most of human history, we could not even precisely define, much less reach. They have directly sampled the environment between the stars, an achievement that would have seemed like pure science fiction to previous generations. As we listen to their fading transmissions, we are hearing from regions of space no human being has ever visited and likely will not visit for centuries to come, if ever. The perspective these spacecraft provide is therefore irreplaceable, a unique vantage point from which to view our solar system and its relationship to the surrounding galaxy. Through their electronic senses, we experience environments utterly unlike anything on Earth, regions where the sun's influence diminishes and gives way to the broader galactic environment. There is something deeply moving about these distant artificial voices speaking to us across the void. They represent the farthest extension of human presence in the cosmos, tiny emissaries carrying our technology, our scientific inquiry, and even our music, art, and greetings in the form of the golden records. They embody both our limitations, in that we cannot yet physically travel to these distant regions, and our ingenuity in finding ways to extend our awareness beyond those limitations. The act of listening for these faint signals also connects us to a broader tradition of cosmic listening that has characterized much of modern astronomy. Since the advent of radio astronomy in the 1930s, humans have been attentive to the various voices of the cosmos, from the steady pulses of rotating neutron stars to the ambient radiation left over from the Big Bang. We have developed increasingly sensitive instruments to detect these natural cosmic transmissions, gaining insights into the nature and history of the universe that would be impossible through visual observation alone. In parallel with this scientific listening, projects like the Search for Extraterrestrial Intelligence have scanned the skies for artificial signals that might indicate the presence of technological civilizations beyond Earth. Though no confirmed detection of extraterrestrial intelligence has yet been made, the continued search represents a kind of cosmic attentiveness, a willingness to listen for unexpected voices from the depths of space. Our own spacecraft, transmitting their faint signals across interstellar distances, provide a model for how such communication might be detected if it exists. There is a certain solitude in these activities, a recognition that space is vast and largely empty, that signals must cross enormous distances before they can be received and interpreted. Yet there is also a profound connection, a reaching across the void to touch, however lightly, regions and environments far beyond our direct experience. In listening for the faint voices of our distant explorers, we extend our awareness beyond Earth, beyond the planets, beyond the heliosphere, into the broader galactic environment that, while alien to our direct experience, is nonetheless part of our cosmic context. This extension of awareness has characterized the entire history of astronomy and space exploration, from the first telescopes that revealed the mountains of the Moon and the rings of Saturn, to the space-based observatories that now peer to the edge of the observable universe. We have continually developed technologies that allow us to see, hear, and in a sense touch environments far beyond our physical reach. Our distant spacecraft represent the current pinnacle of this tradition, extending human presence and awareness farther than ever before. As we continue to listen to these fading voices from the edge of interstellar space, we might reflect on the uniqueness of this moment in human history. For most of our existence as a species, the world beyond Earth was accessible only to the naked eye. The planets were moving lights in the sky, their nature a mystery. The space between the stars was utterly unknown, its properties the subject of speculation and mythology. Now, through our robotic explorers, we directly sample these distant environments, receiving data that transforms speculation into knowledge, mystery into understanding. This transformation does not diminish the wonder of the cosmos, but rather deepens it. The more we learn about the universe through our distant explorers, the more we recognize its complexity, its dynamism, its profound strangeness compared to our everyday experience on Earth. The measurements returned by the Voyagers as they crossed the heliopause revealed unexpected properties of the boundary between the solar system and interstellar space, reminding us that even with our most advanced theories and models, the universe still holds surprises. The approaching silence of these distant explorers invites us to consider what might follow them. New missions are already being planned that would venture again to the outer solar system and potentially beyond, carrying more advanced instruments and power systems. Concepts like the Interstellar Probe or Breakthrough Starshot aim to send spacecraft deeper into interstellar space or even to neighboring stars, extending human presence and awareness still further into the cosmos. These future missions will build on the legacy of the Voyagers, Pioneers, and New Horizons, carrying forward the human tradition of exploration and discovery. They will be designed with the knowledge gained from their predecessors, avoiding known pitfalls and building on proven successes. They will carry more advanced scientific instruments, more efficient power sources, more capable communication systems, and they will extend our presence and awareness still further into the cosmic ocean, sending back new voices from even more distant shores. Yet there is something special about these first voices from beyond our solar system, these initial tentative transmissions from regions never before directly explored. They represent a threshold crossed, a fundamental boundary traversed for the first time. Future missions may venture farther and return more detailed information, but they will follow a path first blazed by these pioneer spacecraft, building on their discoveries and extending their legacy. As we drift towards sleep, let us listen in our mind's ear for these faint, distant voices, these whispers from the edge of interstellar space. Let us imagine the vast distances they have crossed, the years they have traveled, the wonders they have witnessed. Let us appreciate the human ingenuity that designed and built machines capable of surviving for decades in the harshest environments imaginable, still functioning and communicating long after their expected lifespans. And let us consider the profound patience embodied in these missions, the willingness to wait years or decades for results, to build something whose full value might not be realized within a single human lifetime. In an age often characterized by immediacy and rapid gratification, these long-duration missions represent a different relationship with time and achievement, a recognition that some explorations cannot be rushed, that some journeys unfold across generations. The faint voices of our distant explorers remind us that we are part of something larger than our individual lives or even our civilization, that we are participants in a cosmic story unfolding across billions of years. Through our spacecraft, our awareness reaches across the void, touching distant regions of space and time. Their transmissions, growing fainter with each passing year but still detectable with our most sensitive instruments, connect us to the vast, silent realms beyond our solar system. In those silent regions, our spacecraft will continue their journeys long after they fall quiet, long after their last transmissions have been received on Earth. The Voyagers, Pioneers, and eventually New Horizons will drift through interstellar space for millions or even billions of years, potential messengers from Earth to whoever or whatever might someday find them. They carry our technology, our science, our art and music, our greetings and our self-portraits, a representative sampling of a civilization that looked up at the stars and wondered what might lie beyond, that built machines to extend its reach into the cosmic ocean. Perhaps, against all odds, one of these spacecraft will someday be found by another technological civilization, curious like ourselves, about the universe and its inhabitants. Perhaps the golden records will be played, the images viewed, the scientific instruments examined by beings utterly unlike ourselves, separated from us by unimaginable gulfs of time and space. Or perhaps, more likely, our spacecraft will journey forever through the void, undetected, their messages unread, silent ambassadors of a world that once was. Either way, the very existence of these distant explorers and the faint signals they continue to send homeward for now tell us something important about ourselves. In a universe that often seems indifferent to human concerns, in the face of cosmic scales of time and distance that dwarf our individual lives and even our species' existence, we continue to explore, to discover, to reach outward with our machines and our awareness, seeking connection and understanding. The voices from the edge of interstellar space, faint though they may be, remind us of this enduring aspect of the human spirit, this persistent curiosity and wonder that drives us to explore the unknown and to share what we discover with generations present and future. So sleep now, carried by these gentle thoughts of our most distant explorers, drifting silently through the cosmic night, their faint voices still reaching homeward across the vast gulf of space. Dream of the wonders they have witnessed, the planets they have revealed in unprecedented detail, the moons they have discovered, the boundary between the solar system and interstellar space they have crossed. And perhaps, in your dreams, follow them outward, beyond the planets, beyond the heliosphere, into the vast unexplored regions that lie between the stars, silent realms of dust and gas and radiation that our spacecraft now traverse, the first tiny emissaries from Earth to the broader cosmic ocean.